I'm Degenkolb and I'm the design coordinator for the Civil and Environmental Engineering Department. And on behalf of the department and on behalf of the College of Science and Engineering, I'd like to welcome you to the 38th Annual Projects Day. This year, we completed 5 civil engineering projects, 1 environmental science project, and 1 interdisciplinary project that is a combination of environmental science and computer science. So we'll have 2 sessions. The first session will be 3 civil engineering projects, and the second session will have 2 civil engineering projects and an environmental science project. At this time, I kindly ask that you turn off your cell phone or put the phone on vibrate. So let's get started with the presentations. Our first project is sponsored by King County, and King County has been one of our long-term sponsors, and so far they have sponsored close to 20 projects. So I'd like to extend our deepest appreciation to King County for their continued support. So I invite the speakers to the front. And before they get started, I'd like to say a few words about the team. Every year, American Society of Civil Engineers Seattle section organizes a presentation competition, which is judged by a panel of practicing engineers. And the winning team gets to present their project at the May ASC Seattle section meeting, in a meeting. And this year, this team was the winning team of the ASC competition. Introduction and lower it. Testing.
All right, thank you, Dr. G, for that lovely introduction. We are Team CE 25.3, and we had the privilege of working with King County this year on a fish passage design project. My name's Carissa. I'm Paige. I'm Kiana.
I'm Oscar.
And I'm Brooke. So a little bit of an overview of what we'll be talking about today. We're going to touch on our project management structure, then go into our background of our site, and our problem statement, or what our project was trying to solve. Then we'll talk a little bit about our site research that we performed, which informed our 3 alternatives that we developed, then the analysis we did on those 3 alternatives, which led to a preferred alternative that we then proposed to King County.
So like Kara was saying, here's our project org chart. We have King County on the right, SU faculty on the left, and us in the middle. And if you're here today, thank you for being here.
So first, we're going to start with just a little bit of background on the Fish Passage Program in Washington State. Some of you might be aware, but in 2013, there was a federal court injunction for the state of Washington. And a federal court injunction is essentially a federal judge telling the state of Washington that they must complete a certain something by a certain date. And in that case, that something was correcting hundreds of barriers to fish passage across the state of Washington caused by state-owned infrastructure. And this came about due to a lawsuit filed by a coalition of Washington tribes because their treaty rights were being impeded by these fish passage barriers, specifically barriers to salmon, was violating their treaty rights to fish in their usual and accustomed grounds. And a federal judge agreed with the tribes, and as such, state agencies, such as the Washington State Department of Transportation, are responsible for correcting these barriers caused by their infrastructure. And although King County does not fall under that state agency umbrella, they are taking a proactive approach. They have developed a fish passage inventory that categorizes fish passage blockages by how much habitat would be opened up if they were to be corrected. And this has led to 60 high priority barriers that, if corrected, would open up over 300 miles of habitat for salmon.
As for our specific project, we are working on a culvert in South King County, right next to Enumclaw, Washington. The culvert runs next to State Route 410 and underneath the Foothills Trail, which runs parallel to Boise Creek. Our culvert allows our tributary to pass underneath the Foothills Trail into Boise Creek.
And a little bit of site history, because it is relevant for our project as a fish passage project. Our tributary actually runs in the channel where Boise Creek used to run. But in the early 1900s, when they were constructing the railroad and State Route 410, Boise Creek was straightened and moved to run in between those two raised roadways. So as a result, you get a channel that would naturally be moving and have a lot of diversity in velocity and diversity in water depth, depending on where you are in the stream, to a channel that's straightened and more artificial. And this has a lot of impacts on fish habitat, especially salmon habitat, because naturally moving and meandering stream would typically have those areas of lower velocity that are sort of refuge for juvenile salmon. And when you create an artificial straightened channel, you lose a lot of those habitat complexity features.
And now that we've talked a little bit about the King County Fish Passage Program, as well as our specific site location, I'm going to share a little bit why we have been working on this specific culvert for the past year. As you can see here, this is our culvert. There it is. We had the opportunity to do a site visit this past fall, and it really came down to three main reasons why this culvert is not fish passable. The first reason is being it is a perch culvert. So when we went out for our field visit, we measured the distance from the bottom of the outlet to the top of the water surface, and it was about 1.3 feet. The second reason is that it has a wide or very high slope. So from the inlet to the outlet, it's about a 4.7% slope, which leads to really fast velocities going through our culvert. And then the third reason is that the outlet comes out into a really shallow part of the stream. So the fish jumping mechanics from the shallow stream bed up into the culvert is really challenging.
So in order to solve this problem, our team used HECRAS, or the Hydraulic Engineering Center's River Analysis System, which is, not sure why it's glitching, but it's pictured here. And when we go back into our model location, we decided to model this specific portion of the stream, which you'll see in our HECRAS model right here. So you may be noticing that our stream is at the downstreammost section because the flow travels south in that direction. And you may also be seeing a little gray box right around here. That is actually a washdot site in which they're performing a very similar fish passage replacement right there. And whatever they put in is really going to affect all the streams entering our site. So it's really important that we keep that in mind while deciding. And if we zoom in right here real quick, you can see our culvert is in white right there, and right above it is the Foothills Trail. So I took this little video for you all. Hopefully it plays. There it is. So all those cross sections are doing are just making cuts along the stream so that we know how the stream bed looks throughout the channel. And then that way, when we run the model through it, we know that water is going through it. And you can see washdot just upstream of ours. All right, so in order to do our designs, we had to take a bankful width measurement, which is the width of the bank when the bank is full. And that is actually really important for us because anything we design is really going to affect how the water flows through it. For example, at this upper, more circular one, even though there's the same amount of water flowing through that as in the bottom one, the water surface elevation is just a lot higher. So we want to make sure that we mimic natural stream flows as much as possible. And in that case, we need to make sure that the bankful width is wide enough to facilitate those high flows. So when we went onto the site, we got a bankful width measurement of around 5.1 feet. And here's a little action shot of us taking that measurement. And then we plugged that into the Washington Department of Fish and Wildlife Water Crossing Design Guidelines and ended up with a measurement of 9 feet. But we upgraded that to around 18 feet, which may seem a bit high, but that is actually taking into account a lot of climate change that will happen in the future, and that's also taking into account tribe preferences.
All right, so we have our fish passage program background, our problem statement, our bankful width, and some site history. The last thing that we need to finish our model is to actually figure out how much water is going through our culvert. So as you can see on this slide in the red over here is a basin delineation, which WashDOT performed. We were lucky enough to be able to have access to that information. So they performed a basin delineation, they calculated flows. We also performed a basin delineation, which should be in blue. And then you can see when I flip back through these, the differences, the similarities. And then if we move forward, we actually got an equation from the King County Surface Water Design Manual. Sorry, spoilers. And we were able to scale their equation, or scale their flows, sorry, to our site, and we actually figured out what our flows were. So one last thing to explain down here is the 100-year flow. So you can think of this as the 1% chance of the amount of flow that would happen. So it's basically like 1 in 100 years, what would that storm look like? Not to say that once in 100 years that will happen, it's just how we describe it in engineering. And this is really important for the rest of our modeling, so make sure to keep an eye out for that.
So now that we know the amount of flow going through our culvert, we're able to put that into the HEC-RAS model, which Kiana explained earlier. And on the screen right now in blue, you can see the existing condition during the 100-year flood. And an important thing to note is that up here, this washed out site, this existing condition is already considering the structure they're planning to put in, since they're planning to put it in before construction would begin on our sites. And when we go to a cross section here, and we zoom in on ours, there's two major problem points to note. At the inlet, there's this backwater that's effectively showing you that there's too much water going through the culvert for its size, so it needs to be larger. And over here, we have this hydraulic drop. That's that 1.3 foot drop that we mentioned earlier. And both of these points are not very conducive to fish passage. So to address this, we proposed 3 alternatives to our liaisons at King County. And those are a pipe arch, a bridge, and a box culvert.
So that first alternative was the pipe arch. This would be a concrete pipe arch. And here you can see our 10% conceptual design. Note the 18-foot width to accommodate that bankful width that we calculated, and the 6-foot height from the stream bed to the top of the structure to give sufficient freeboard during that 100-year flow. And the great thing about having our HEC-RAS model is once we've developed it for our stream, we can then put in proposed structures where there's our current culvert. And this just sort of shows us how the flows would be moving through a structure with those dimensions if we were to construct it. And so here you have our pipe arch, and you can see the water surface elevation for that 100-year flow.
And then the second alternative that we ended up proposing is a bridge. So, oh, there we go. And then these are our 10% conceptual drawings as shown before, and then I'll just draw your attention to the 20-foot width, which we increased from the 18-foot prior. And then this is the outlet of our hydraulic model for the bridge, and then I'll also draw your attention to that vertical gap for our bridge as well.
Then finally, we have our 4-sided concrete box culvert. Even more spoilers. Here are HEC-RAS results. Those are pretty cool. We actually turned to an 18-foot width for this, similar to the pipe arch instead of the 20-foot bridge.
So once we had those 3 alternatives developed, we wanted to evaluate them. And so we did this using a evaluation matrix. We took 9 different categories that were relevant priorities for our project, and we weighted them based on importance. And then we went through and we scored all 3 alternatives, both qualitatively and then quantitatively, as well as just an as-is option just to give us a baseline. When we did this, we found that the box culvert and the bridge came out ahead with very similar scores. The box culvert just came in a few points ahead of the bridge, so we went to King County to discuss.
And while the box culvert and the bridge had very similar results, as you may have seen, we chose the box culvert. The reasoning behind this largely is because of certainty within the cost estimate. So while both of these alternatives require structural analysis, there hasn't been a geotechnical analysis completed at the site, so there's a lot of variability, for example, within the foundation design and the structural design, and the bridge would have more variability than the box culvert would. And since there's more uncertainty there, we went with the box culvert. And with that decision, we're able to move on with our 30% design. So on the screen right now, you can see the existing plan. And one thing to note here is this temporary stream diversion. You may be wondering, what is a temporary stream diversion? And pretty much, when you're doing construction in a stream, you need to get that water out of there so that the construction workers don't have to get wet, because it wouldn't be very fun for them. However, this is a fish passage stream, so you may be wondering, what happens to the fish? Well, pretty much, we just put up nets, and they can't get sucked up into the pipe, since they wouldn't like that. And they hang out there for the duration of construction, which likely won't be very long. As for our proposed plan, the main difference you can see here is that it's much wider. So this is that 18-foot width that we mentioned earlier, as opposed to the previous has a 4-foot diameter. For the cross-section, you can see a bit more of the design. Important things to note here is this 3-foot bearing pad. As I mentioned, there hasn't been a geotechnical analysis yet, so this is a conservative estimate. It may become smaller and cheaper. However, this is fair to assume for now. Additionally, we have the stream design within the culvert. This is designed so that it can accommodate both the low flow and the high flow conditions.
So now returning to our hydraulic model, we can really see how the flows would be affected by this new structure. So here is the side view of our proposed conditions. Once again, you can see those two hydraulic drops. And when we transition to the structure with the wider width, you see that those flows, those two drops disappear and the flow moves much smoother through that culvert. And here as well, when we look at the velocity heat map that HECRAS generates for us, these are our existing conditions. We're seeing very high velocities moving through this culvert, some approaching 7 feet per second. And when we transition to our proposed structure, you see that those velocities go way down and you have areas of very, very slow moving water, which is much more conducive to fish passage, as well as just a much more enhanced habitat for juvenile salmonids that are going to be racing the stream for years to come. Thank you so much. Any questions? You just put up your hands.
I have a quick question regarding opportunities for collaboration between King County and SDOT. You mentioned that they had another project going on very close to your site. Is this something that you saw as a key challenge in your project? I know you had to consider a lot of the implications of their project in what you were conducting. Did you see an opportunity to collaborate with them, or I'm just curious if you think that.
So your question, we're just going to repeat it so that people online can hear. So your question was if we were able to use this project as an opportunity to collaborate with WashDOT because their project was right upstream from ours. And we saw it as a really great opportunity and a benefit to us because they had already completed their report for their preliminary hydraulic design. So there were actually a lot of really, really helpful information about our tributary in that report. King County was also in communication with WashDOT, so we got some information from them that we couldn't have gotten otherwise. So it was really helpful actually to have that as a resource for us.
What model did you use to incorporate climate change projections into your design?
Yeah, I can take that question. So you asked what model we use to include climate change in our design. We actually use a tool made by the Washington Department of Fish and Wildlife called the Climate Change Tool. Very fitting for the name. But that was very early on in our design process. We actually just used it. It gave us percentages for how the flows may change in the future. So we just kept those percentages in mind during the design process.
So I'm not a civil engineer admittedly, but the HEC-RES that you guys were using seemed pretty cool. I was wondering if you guys could speak to how that data was collected or where you found that, and how you guys used that and how that process went.
I can take that question. So the question was how we use HEC-RES, the data that was used to input into the model, and just kind of our overall experience using it. And to be completely honest, this was our first time any of us had used HEC-RES. And King County was very, very gracious in hosting many learning seminars, often on a Saturday. So we had the opportunity to learn a lot, and we ended up using the 1D model. And a lot of our factors that we inputted was just based on our structural design and current flow patterns that we had observed in the field or had calculated through some of our water design manuals.
Are there any sections of spawning right there?
That's spawning has been observed through the Boise Creek, so it's assumed that that would continue into the tributary if these blockages were corrected, but they've done quite a lot of restoration along this creek because we do have multiple species of salmon that have been confirmed to be spawning and living in the Boise Creek.
Are you planning like certain gravel and stuff for?
Yes, so you asked if we're planning to use certain gravel, and we are planning to put in a medium-sized stream bed mix. We completed a pebble count initially to figure out what the existing conditions are. However, since this was a highly modified site, the existing stream bed material is actually largely railroad material. And so we and WashDOT upstream both decided to go with the medium-sized standard stream bed material as opposed to the existing material.
Yeah, great job. I really like the focus you had here. Kind of a follow-up question on the salmonoids. You did a great focus in getting the structure built in that. Did you have to deal with any of the runoff, any of the stormwater runoff issues or any of the chemicals therein? Or that might be a whole nother look at that.
So you asked if we had to worry about, like, for example, stormwater runoff and chemicals, and honestly, no, that was not within our scope.
And then if I could add on to it for just a little bit, our stream it's not very much in the path of a lot of those, and I believe the Boise Creek at least is very deep away from our stream, even though it goes into it. So I don't think you'll see a lot of those. Hopefully not.
One last question.
You guys are talking a little bit about stream bed analysis. Typically, you like to use a little bit of density of motion determination. Did you guys do any of that?
Yeah, so forgive me, I understand your question, but I don't know if I can repeat it word for word. But you asked if we did like turbulence, like, and we with the stream bed material, if we did calculations to back up that decision, is that right? Yeah, so we did discuss that a little bit with King County, but we didn't end up doing calculations just because we had the WashDOT stream bed mix already. They made that decision and we wanted to keep it consistent, so we felt that it might be redundant.
Thank you, Dean. Yeah, it's institution, Now we move on to the conversation. And thank you, Keta. They have seen a long time concept. So thank you, Keta. They have a delight with that and we want to keep.
Hey everyone, we are CE 25.5. Our project is SEA-TAC Lights, North Service Center, it's seismic evaluation, upgrade. My name is Harold, it's Paula, Lillian, and Nick. Here's a general outline of our presentation. We're going to talk about the background of the North Service Center, followed by the team's evaluation process, concerns we found in the evaluation process, and finally we'll finish off with the team's recommendation and cost estimate. Here's our project team structure. We have our liaison, Robert Cochran, and Grace Barrington, followed by our project coordinator, Dr. G, faculty advisor, Chris B, and the rest of us make up CE 25.5. I'll pass on to Nick. We'll talk about the background of the North Service Center.
Thank you, Harold. The North Service Center is located in Seattle's Licking Springs neighborhood. This is just 8 miles north of campus. This The North Service Center is a crucial facility that is responsible for maintaining large portions of Seattle's power grid. Places like the North Service Center house not only essential parts and equipment like cable stock and transformers, but also the large fleets of trucks and crews that respond to outages around the clock. Without places like the North Service Center, getting the lights back on quickly would not be possible. While the operations that come out of this facility are essential, the structure itself may not be fully prepared for a seismic event. If this building were to fail, it would delay emergency response, pose a risk to the inhabitants of the building, and ultimately leave large portions of the city without power for longer than necessary. Homes, hospitals, fire departments are all relying on Seattle City Light for a rapid response following an outage. Because North Service Center would not be able to serve the city if it were to fail, Seattle City Light wanted to further investigate how the building would perform during and after an earthquake. And this leads us right to our problem statement. Seattle City Light has tasked design team CE 25.5 with conducting a seismic evaluation and preliminary seismic upgrade of North Service Center's buildings E and A. This is to address structural deficiencies and mitigate seismic risks. Now Paula is going to take us through the evaluation process.
Thanks, Nick. So the evaluation process highlights the key stages that we went through, designing the final upgrades for both buildings. So first, during fall quarter, we used the ACE 41-23 manual and performed the Tier 1 screening process by reviewing checklists to identify structural deficiencies. Then, we calculated the demand to capacity ratios by directly comparing the demand values and capacity values specific to that element. This method allowed us to quantify the extent of retrofitting required for each deficiency. We also learned that under the Seattle existing building code, we are permitted to use a different design standards apart from ASE 41. Therefore, our team utilized the ASE 7-22 standards to design the final upgrades for each building within our scope. To elaborate more on what our team did during the Tier 1 screening process, we completed a series of checklists designed for different performance levels, such as the immediate occupancy and life safety. So both of these performance levels ensure that the North Service Center sustains minimal damage during an earthquake, while protecting occupants inside and outside of the building and remains fully functional immediately afterwards. Presented in your screen is what a checklist looks like. And these are tailored to specific structural elements within the lateral force resisting systems of both the auditorium and the warehouse. In order to complete these checklists, our team conducted site visits, performed preliminary investigations, we took photographs, and meticulously reviewed site plans to verify conformance with the building's existing conditions. So this example on your screen is tailored to the unreinforced concrete masonry shear walls at the warehouse. As you can see, some parts are marked as ENSC, which stands for non-compliant, suggesting that this wall is deficient and requires further analysis. I'm going to pass it back to Nick to give you guys an overview of the deficiency findings.
Thank you, Paula. Following the Tier 1 screening process, the team was able to understand the magnitude of the situation. All but one of the North Service Center's structural elements lacked the capacity to withstand its proportion seismic load. While the team had anticipated a handful of deficiencies, we expected more items to come in compliance with ASE 41. Shown is the demand capacity ratio table. While any ratio greater than 1 is of concern, we had many members go into double digits. Also shown is the plan view of the auditorium and warehouse with the locations of all the deficiencies the team was able to find. But let's take a closer look at some specific examples.
Diving deeper into the areas of concern in the auditorium, Team CE 25.5 has identified significant deficiencies within the lateral support system. This includes in-plane and out-of-plane seismic forces acting on the existing shear walls. Currently, there are only 2 shear walls within the auditorium, one on the south wall and one on the west wall. The south shear wall is made up of reinforced concrete and has a demand versus capacity ratio of 1, making this wall compliant. In contrast, the west shear wall is made up of CMU, which stands for concrete masonry units, and has a demand versus capacity ratio of 1.8, making this wall insufficient and will likely be compromised during a seismic event.
Now I'll pass it back to Paula, who will describe a deficiency within the warehouse. Thanks, Elaine. So in the event of an earthquake going in the east-west direction, the shear wall at grid 7 is subjected to seismic forces from both buildings. Given the extensive tributary width coming from the warehouse, the shear walls at grid 7 and grid 25 may not provide sufficient lateral resistance. To address this deficiency, our team has developed an upgrade to propose to Seattle Light, which we will introduce later in the following slides. But for now, I'm going to pass it to Harold to share another deficiency we found at the warehouse.
Thank you, Paula. In continuing the conversation in the warehouse, our team identified two major deficiencies in the diagram. For clarification, a diaphragm is a structural component which is part of a building, which can either be the roof or floor system. In the case of our warehouse, we analyzed the steel deck diaphragm, which is our roof system. The first major deficiency our team identified is our team identified are the insufficient walls. From our site visit and looking through the building plans, our team found that the existing walls from the decking to the trusses and also the longitudinal seam wall shoulder and gold to be insufficient from our analysis and inspection. In general, these walls transfer forces and help connect existing members. The second deficiency our team identified is the shear transfer. The current truss configuration of the warehouse are spaced every 20 feet, and within these 20 feet are these steel blockings shown in red. These steel blockings transfer shear forces from the decking to the overall lateral resisting elements. However, again, from our analysis, we found these to be insufficient and further upgrades would need to be done on the diaphragm. I'll pass it back to Nick, who will talk about the SEA-TAC existing building code.
Thank you, Harold. Once the team was able to understand all of the deficiencies throughout the North Service Center, the originally proposed approach of utilizing ASC 4123 to conduct a retrofit appeared problematic. The associated costs and level of effort required to follow this method greatly exceeded our initial expectations. To lower these costs and maintain project efficiencies, the team wanted to explore alternative methods. We learned that through the CL existing building code, the team would be able to utilize ASC 722. But this means we would now be designing new elements to implement into the North Service Center structural system, as opposed to retrofitting the existing ones. Also, because of the specific lateral force resistant system that is featured in the North Service Center, there's an opportunity to utilize FEMA 1026. Our Tier 1 screening process revealed to us that we can classify the North Service Center as a rigid wall, flexible diaphragm structure, and this had important implications as we designed some of our new elements. Now, let's take a closer look at some key upgrades the team was able to design this year.
To fully address the deficiencies on the west wall and the auditorium, we have designed an upgrade to strengthen the existing CMU wall. The plan is to install an 8-inch concrete wall against the existing CMU wall for structural reinforcement. The primary objective is to enhance the load-bearing capacity of the west wall through the addition of a stronger concrete wall against the weaker CMU wall. This will allow the load to transfer and dissipate into the stronger concrete addition without any failure modes occurring. Now, Paula will describe an upgrade in the warehouse. Okay. To evenly distribute seismic forces in the east-west direction, our team proposed to install 3 sets of the new truss and brace frame system at the center of the warehouse. Plan U indicates their respective tributary areas and placement, where one will be placed offset by grid 13, one at grid 17.5, and one at grid 21.5. Section view illustrates the new system, featuring a new truss on top with 2 brace frame attached to its bottom cord. We also use SAP 2000, which is a structural analysis and design software, to create a virtual model of this upgrade and evaluate the internal forces within the new system. This tool allowed us to simulate how the new truss and brace frame would respond to earthquake forces. And from this analysis, we determined the internal forces within each member. Then we applied these forces into the compression and tension equations from the steel manual to calculate the minimum cross-section required for each steel component. Additionally, we have dampers attached at each brace frame connection, with a gusset plate connecting the brace frame members to the top plate of the dampers. They will also be mounted onto the slab of the warehouse using base plates and anchor bolts as part of the installation process. The design specifications of the dampers are provided by Seattle City Light, and the purpose of these dampers are to act like shock absorbers in a car, helping to soften the shaking of the building during an earthquake, and reduce the damage on the overall structure. I'm gonna pass it to Harold to share another upgrade for the warehouse.
Thank you, Paula. One of the major upgrades that the team proposed for the diaphragm of the warehouse is the addition of light gauge Z blocking. As I mentioned earlier, shear transfer and insufficient walls are issues that need to be addressed. The proposed upgrade, shown in orange, will be located between the existing decking and trusses, and also at the proposed raised rim and truss configuration that Paula just mentioned. Here's a sample of our existing condition, and here's our proposed upgrade shown in pink. The connection is as follows, where the top of the Z blockings will be drilled underneath the steel deck with tech screws, and the bottom of the Z blockings will be connected with power actuator fasteners to the top cord of the existing trusses. The proposed upgrade improves the connection and allows lateral forces to effectively transfer from the decking to the overall lateral resisting elements, which leads me to the full breakdown of all of our proposed upgrades for both the warehouse and auditorium. To further quantify each upgrade, here are all of our concrete upgrades. Following all the concrete, here are all of our diaphragm upgrades, which includes tech screws, Z blocking, and C channels. And finally, here are all of our steel upgrades, which include brace vents with dampers and ones without. All of these upgrades follow the general procedure of doing a tier 1 screening process, a DCR analysis using ASC41, the use of FEMA to better understand the seismic behavior of a rigid wall flexible diaphragm, and finally using ASC7 for our proposed upgrades. I'm passing on to Helene, who will finish off talking about the cost estimate of this project.
To fully quantify the scope of this project, costs must include material and labor costs. This includes all our structural upgrades mentioned in our mitigation plan. Our detailed cost estimation is broken down by required corrective action, unit cost, material quantities, and associated labor hours. All our values obtained were provided by us by our liaisons at Seattle City Light and confirmed by our faculty advisor. Thank you so much for paying attention to our presentation. We'll love to take your questions now.
You talked a little more about why you used ASC7, which is for new design, versus ASC41 for existing buildings?
So the question was why we were able to utilize ASC722, which is usually used for new designs. This is because we wanted to design new elements to be implemented into the existing structural system. So we're not aiming to strengthen the existing elements, we're trying to implement new elements into that building, and this would follow ASC722. If that answers your question.
Well, 41 allows for new elements as well. So just open for more background on the decision.
I can add on to that. So when we did the ASC41, did a tier 1 screening process, our team realized the extensive work that needs to be done using ASC41, and for cost efficiency for this project, our team realized we can go back to the SEA-TAC existing building code and look at the references. And one of the references allowed us to use either ASC41 or ASC7. So our team decided that rather than using all of the existing conditions, we are proposing these new substantial upgrades to greatly improve this building. That's why.
Was there ever the alternative thought just that like the cost to completely tear it down and create a new building?
Thank you, Mr. Chanchorn. This was something that was brought up, but it's kind of out of our scope. To fully make that decision, Seattle City Light needs to understand how much it would first cost to retrofit the building and improve its existing conditions. So that's kind of out of our scope and for Seattle City Light to decide, but this project will certainly help them make that decision.
What are some of the challenges that your team faced during this project?
I'll restate the question. Thank you for your question. It was, what are some of the challenges we faced during this project? This was a massive project for 4 undergrads to undertake with no seismic engineering knowledge or experience. So it definitely, when we got this project, it was like, all right, what is ASC even? Let's know what where do seismic forces even act on a building? So it definitely has been a big journey and a big, big thank you to our liaisons and faculty advisors on sitting with us on weekends for hours and during weekdays to, give us equations and sit us through and understand how, seismic engineering actually affects buildings. So lots of challenges. Also our scopes changed throughout this project because it was such a massive project, including the warehouse and auditorium. So we had to shift the scope as we went through. But our gracious project coordinator and again, our liaisons and our advisors had worked with us through that. So thank you very much. Yeah, it's been a good, fun project.
Any other questions?
This might be a bit out of your scope, but how did you have to consider the current use of the building into your upgrades and how they'd impact, like how the building could be used?
So because, like I specified earlier, this is a central facility that is being relied on constantly to maintain Seattle's power grid. With that said, these upgrades are intended to not be obstructive to the work that the Seattle City Light has to do inside the warehouse from a day-to-day basis. So like using brace frames instead of a new concrete wall, that was intentional in the sense that if we put a new concrete wall right through the middle of the warehouse, it closes off a lot of access to all the parts, forklifts can't drive through, stuff like that. So it was something that we heavily considered throughout the evaluation process. Yeah, thank you.
No more questions? Thank you. Okay, we move on to our presentation. Our presentation is one. It was done for community road housing, and they will talk about community road housing. And this project was sponsored by Degenkolb engineers. So we have completed 2 projects for community road housing, and Degenkolb has partnered with us for 2 years. So thank you to Degenkolb for their continuous support to us. And with that, I give it over to the team.
Right, we are engineering design team CE-25.2, and our project is a seismic evaluation of the villa apartments.
I'm Keon. I'm Will.
Shay.
I'm Kirtana.
And I'm Nick. Today, our presentation will cover 6 key topics. We'll begin with our project background, then move into the retrofit pathways which we analyzed. We'll discuss the first steps of our project, the A6 qualification criteria, the A6 seismic improvement methods, and finally, the cost estimate for our work. Will is going to begin with the project background.
So for an overview of our project team, from Seattle University, we have our faculty advisor, Professor Michael Ray, as well as our faculty coordinator, Dr. Deeb. Then we have our sponsor, Community Roots Housing, as well as our technical liaisons from Degenkolb. A little bit more about our sponsor, Community Roots Housing. We're a local nonprofit founded here in Capitol Hill back in 1976. Today, they house over 2,000 residents in nearly 50 different properties, and all of their properties are low-income housing. You can see just some of them on the map here with our site, the Villa Apartments in the center. And here's our building, the Villa Apartments. It was originally built in 1909, and here it stands today on the corner of Pike and Boyle. Our building is an unreinforced drone footage, but it's an unreinforced masonry building with wood diaphragms, meaning it is the structural brick has no steel reinforcement, making it extra vulnerable to seismic events. In the 1990s, our building got a major addition added on. You see it outlined in red here. It was not part of our project since it's seismically separated from the rest of the building. Alongside this addition, we also had some seismic renovations done, including the addition of 2 chevron brace frames, as well as wall anchorage and parapet fixing. Now I'll pass it back to Nick to go over our retrofit methods.
Thanks, Will. Before diving into the specific calculations and design work that our team performed, it's important to understand the scale of this problem. The city of Seattle alone has over 1,100 unreinforced masonry buildings, all at risk to damage during a seismic event. Because of this, in 2024, the city of Seattle passed Resolution 32033, which created a program to incentivize the retrofitting of unreinforced masonry buildings. Generally speaking, when you retrofit an unreinforced masonry building, you protect life safety, you preserve historical landmarks, you minimize financial strain on communities like those in our apartments, and you improve earthquake resilience. For our project specifically, the purpose is to perform a seismic evaluation to voluntarily retrofit the Villa Apartments and comply with Seattle Existing Building Code. This led us to use the 2021 Seattle Existing Building Code, Section 304.5.1 methods for retrofit compliance. Within these methods, there are 3 sub-items, as seen on the screen below. Initially, our team looked into item 3, for existing retrofits, where we aimed to qualify the 1990s retrofits as acceptable in today's standards. However, we determined that they were not feasible. Then we looked into item 2, section 304.4.2, reduced IDC method, which is a full life safety upgrade of the building. We determined that this was too expensive for our client, and as such, it was not feasible. This led us to pursue item 2, the Chapter A6 alternate method.
Chapter A6 is a retrofit method specifically for unreinforced masonry buildings, and this allows us to remain cost-effective by minimizing the required life safety upgrades. This is especially important for us because it allows us to find a design solution that aligns most with our client's goals, being to remain cost-effective, limit tenant displacement to under 12 months, and minimize the amount of invasive structural replacement. Now I'll pass it to Keon to talk about our first steps.
So as Shay and Nick just mentioned, the most preferable retrofit pathway is the alternate method. But before we could begin the qualification process, we had to assess aspects specific to our building, starting with a material analysis, giving us our seismic weight, alongside determining the seismic hazard, giving us the shear forces, both of which were necessary before any further evaluation. Starting with the material analysis, on the left is a cross-section of our exterior wall showing that most of the material is masonry, but we also had to account for other material like wood and cement plaster finish. And on the interior, on the top right, are 2 of the many interior walls we considered. On the bottom right is interior floor diaphragm, giving us all the materials we need for the analysis. So we took those materials and found their unit weights using the appendix of ASC 716 alongside previous projects and other online resources. Now looking at the seismic weight using those unit weights. On the left is a cross-section of our north wall, the second story highlighting half the distance above and below that level. And putting that in plan view, we can see the weights, and that most of the weight is coming from the perimeter of our building, highlighting the significance of masonry in our project.
For the seismic hazard analysis, we used the ASCE 716 hazard tool to get our key seismic design coefficients using soil type C. Since we do not have an official geotech report, our team prescribes that a geotech investigation be done for our site. Since this is also an existing building, Chapter A6 allows us to reduce our seismic forces to 75%. This helped us get started on the building demand calculations, the wall story force, and shear. The wall story forces were calculated for each wall corresponding to each seismic level. To get the wall story shear, we just summed up all the wall story forces at each level. Next, I'll pass it on to Shay, who will be talking about the A6 qualification criteria. A6 provides us with 7 criteria which we must meet in order to retrofit the villa apartments per this method. And of the 7 criteria, criteria 3, 4, and 7 required a bit more work. Criteria 3 has to do with the weak story vertical irregularity in the commercial space of our building. Criteria 4 has to do with the mortar shear strength, which will require out-of-scope testing. And criteria 7 has to do with the way that our masonry walls are responding to seismic forces. Starting with criteria 7, we were led to do a pier analysis in which we aimed to prove that all qualifying piers made up no less than 40% of the total wall's length. Piers are sections of brick in between windows with no openings, and the ones highlighted in green are those that we can count towards our analysis. After doing these calculations, we found that we did not meet that 40% rule, thus leading us into our exception. Our exception had us do a masonry analysis via Appendix A1 Special Procedures, in which our first step was to determine which pier failure mode controlled at each level on each side of the building. The first pier failure mode is sliding failure, which occurs when the lateral forces exceed the frictional resistance built between the brick and the mortar, causing sections of brick to slide against each other like this. And the next type of failure was rocking failure, which occurs when the overturning moment from the lateral forces exceeds the self-weight of the building, causing sections of brick to tip back and forth along a single axis like this. Ultimately, once we figured out which pier failure mode controlled, we were able to use the correct demand and capacity equations. And something important to note here is that A6 allows us to have a demand to capacity ratio of up to 2.5, whereas the industry standard is typically 1. This means that our demand can be up to 2.5 times our capacity.
To visualize the demands we considered for the masonry analysis, this is a west elevation of our building highlighting the different pier sections and the forces acting on them. As we descend in elevation, the demand increases, resulting in the highest demands occurring on the first story piers. As for capacities, this is the same elevation highlighting how we considered the dead loads acting on the individual piers. And similarly to demands, the dead loads increase as we descend in elevation, contributing to the greatest capacities occurring at the first story. And our job was to ensure that these piers could withstand the high demands, and we concluded through our analysis that all pier sections on all 4 sides of the building were within the 2.5 demand capacity ratio provided by the alternate method, thus concluding our criteria number 7 analysis.
As Shay mentioned earlier, criteria number 3 has to do with a weak story vertical irregularity. Our team determined that the villa apartments has a weak story vertical irregularity in the window wall on the south-facing first floor of the building because the window walls have less strength or stiffness than the masonry walls above them. In order to analyze this weak story vertical irregularity, our team looked at the drift and strength capacities of the wall. Drift is how much the wall moves from side to side during an earthquake, and strength is how the wall reacts to seismic forces, like those Kirtland discussed earlier. Because the villa apartments currently has chevron braces on the south wall that were installed in the 1990s, our team analyzed these first for their drift and strength capacities and determined that they were both inadequate. As such, we recommend the installation of new buckling restrained brace frames to make the window wall adequate and reduce it from being a weak story vertical irregularity.
As Nick mentioned, the system that we're designing is called a buckling restrained brace frame. This is a brace frame that is designed in a way that the brace yields both tension and compression during a seismic event. This is achieved due to the grout field, like seen in this picture, that surrounds the steel core that prevents it from buckling. This is not typical when compared to normal brace frames, which are weaker in compression than they are in tension, but BRBFs are the same in both because they do not buckle. Here's our finalized brace frame plus building details that our team proposes. We do recommend more building probing and extensive geotech work be done at our site for a finalized foundation design.
Once we had finalized the tentative design of our system, we placed it into SAP 2000, a structural analysis modeling software, so that we could apply our seismic forces and check the system for that drift and strength mentioned earlier. As seen on the left is our west frame with accurate member sizes in the modeling software, and on the right is the west frame in deflection, so those forces have been applied, and we can see how much it moves during a seismic event. We determined that the system was adequate in both drift and strength, which is great, and allowed us to finalize our design, as seen above, with accurate member sizes for the beam, columns, and braces, as well as our tentative foundation below. Because the system is adequate in drift and strength, this allowed us to check off criteria number 3 and move into the seismic improvement methods, which Will is going to discuss next.
So the first seismic improvement element that is outlined by A6, out of plane wall bracing. This is basically used to prevent the walls from collapsing in between floors and can implement use of the bracing shown on the right here. Since this wasn't part of the 1998 retrofit, we first had to find out if our building would require this, which is done by measuring the height to thickness ratios of each wall and comparing them with allowable values found in A6. After doing so, we found these three areas of the building that exceeded this H/T ratio, which usually would mean that we would have to install the out-of-plane wall bracing. Instead, since these two walls are where a veneer layer of brick is present, our solution to this is to tie the veneer brick into the structural brick with use of these Python C anchors. These can be simply drilled into the exterior, tying the veneer to the structural brick, creating one composite out-of-plane behavior. And here's a video from Python demonstrating the effectiveness of their Python C fasteners. See the veneer layer is on the left and the structural brick is on the right. Pretty cool. Next is the next seismic improvement element outlined by A6 is wall anchorage. Wall anchorage is basically used to tie the floors to the walls, preventing them from completely separating and collapsing in a seismic event. To evaluate these wall anchors, since they were part of the 98 retrofit, we had to evaluate them for both shear and tension or in-plane and out-of-plane forces. First, we evaluated them for out-of-plane or tension forces and found these areas of deficiency of the building here. This is just one example of the second floor plan. We're recommending new anchorage at all of these locations. Additionally, where we cannot install new anchors, we have to recommend a special lateral bracing for areas like the stairway and the elevator shaft. Next, we evaluated the anchors for their shear or in-plane capacities and found these areas of deficiencies here. Lastly, Shay is going to go over parapets.
So the first step in evaluating our parapets was to calculate height to thickness ratios, and we found that all of the areas that would need bracing already had it. And so our next step was to determine whether the capacities of these four elements met the required demands. After doing calculations, we found that the capacities did meet the demands, thus our parapet bracings are sufficient as they are. And this concludes the seismic improvements that would allow the villa apartments to be considered a retrofitted masonry building. Moving into our cost estimate, we broke our cost estimate up into 4 categories, 1 being design fees, 2 being Chapter A6 qualification requirements, 3 seismic improvement methods, and 4 our contingency and overhead. Overall, our total project cost came out to $1.1 million. And something important to keep in mind here is that A6 is the most cost-effective method in comparison to other retrofit methods, such as substantial alterations. Thus, we believe that our design solutions are most in line with our sponsors' goals. Thank you.
Awesome presentation. Just had a quick question. As a former dirt guy myself, what led you to choose site class C versus site class D, since site class D would give you guys a little more conservative values?
So I'll repeat the question. The question that was asked is, why did we choose site class C? Is that correct? Well, we do not have an official geotech report, like mentioned, so we had to use existing boring logs through our Washington Geological Portal with the advice of a senior geotech from a different company. And we were able to look at the soils and came up with the idea that it is soil type C. So we're just basing it off of that. And I did repeat that we are recommending, we need a geotech investigation to be done for our site, which will also be useful for our finalized foundation design.
Can you explain why you're allowed to get to 250% of your, you can have your demand be 250% more than your capacity, and also how you feel about that?
So the question was, why are we allowed to use 250% demand compared to the capacity of our building? How do we feel about that? Our main reason why we're allowed to use a DCR, or demand to capacity ratio of 3.5, is because of the Chapter A6 alternate method, which allows for a minimum level of life safety standard in our upgrade. Compared to a full life safety upgrade, this is a more cost-effective method that aims to reduce the cost on especially low-income housing in the city of Seattle, like the villa apartments, thus allowing us to design our building to still maintain life safety in an earthquake, but possibly not be usable after that seismic event. We definitely feel good that this is maintaining affordable housing in the city, and are confident that our design meets the necessary standards. I feel pretty good about it.
Just wondering if the newer building had a geotech report that you could look at.
The question was, did the renovation in the 90s have a geotechnical report that we could look at? We were not given a geotechnical report from the new building, and especially because we were only analyzing the south side of that old building, they wouldn't have performed any borings where our foundation work would be done. So we still recommend that they do additional boring work, even if they used it in the past.
Any other questions? Yeah.
So you said the building was originally built in 1909. Is that correct? Yeah. So what sort of existing building information did you have in terms of drawings or materials, or did you do any site investigations to kind of confirm any of that?
Something that was actually really interesting about this project, at least for us, was we only got as-builts from the retrofits done in 1990, so we had no original building documents. This was something that I feel like we initially kind of struggled with in the beginning, especially after going to the site and seeing some things that were a little bit different from the plans. So definitely a learning curve. In terms of information that we had on our building, I mean, it was kind of just whatever was in the structural notes and the general notes. And yeah, does anyone add anything else?
We definitely, I mean, I didn't know before that the building plans wouldn't match exactly what was there. So like we found that out the hard way, like looking for wall anchorage that wasn't there. So yeah, we wish we had better drawing, but we had what we got from 1998.
Thank you, team. This concludes our first session, and instead of people in the audience who are kind of wondering how you can partner with us on projects, come and see me or see one of the faculty members. We are looking for projects for next year. So this is a good opportunity for you to see here. And you know, we can another
No, absolutely
Our first presentation of the second session, the project that was done for Black Farmers Collective. And this project is a community benefit project, just like the previous one, the Villa Apartments. The project was sponsored by KPFF Special Projects Division, and Black Farmers Collective is a returning sponsor. So this is the second time we have done a project for them. And KPFF Special Projects Division has been kind enough to sponsor a project for the second time. They sponsored a previous community benefits project for us. So thank you for your support. So with that, I give it over to the team.
Hi everyone, how are you? 13 CE 25.1. We're working with the Black Farms Collective in KPFF Engineering Consulting for an accessible ramp design for Yes Farm. I'm Nathaniel.
Elena.
So, I'm Sloan.
I'm Patrick.
Here's an organization chart of our project liaisons, Seattle University faculty, and our design team. Our main client is Ray Williams, and he's the representative of Black Farmers Collective. We work with KPFF civil and structural engineers, along with environmental works. Our faculty advisor is Dr. Riazi, and our design coordinator is Dr. G. And our design team consists of the 5 of us here today. So for today's outline, we'll first go over the site background, then move on to minimum requirements. We'll follow with the design process of the ramp, and then some time for some questions. Nathaniel will start us off with background. Thank you, Sloan. To give some context on our client, the Black Farmers Collective, they're a nonprofit organization with the mission to create a Black-led food system through land acquisition, facilitating education, and creating spaces for Black liberation. For example, our site is from as shown here. Here's a vicinity map. Highlighted in blue is Yes Farm. This is 1.5 acres large, located on Nestor Way, just 5 blocks south of campus. Here are some images of our site, highlighted in yellow. This is the direction from the sidewalk to the main entrance of the farm. And as you can see here, you can see there's a steep slope. And as we're starting, there'll be a 3D model being handed around. So this slope creates a problem for individuals with mobility disabilities to access the space. This leads into our problem statement. So due to the inaccessibility, we have been tasked with designing an accessible ramp design for Yes Farm, and we have created a 30% design package as well as a cost estimate. Some of our design challenges are the trees. There are 5 large trees located on site, so we don't want to inhibit on their roots or their health. Also, as mentioned before, the slope of the site is currently 20 to 25% grade, and in terms of ADA compliance, we want to get that down to 8.33%. Lastly, we have right of way. Our site will be located here, highlighted in orange. This area is owned by the Seattle Department of Transportation, whereas the remainder of the farm, highlighted in blue, is owned by the Washington State Department of Transportation. Here's a drone video highlighting the site. So as you go look at the model being handed around, if you want a bigger, larger scale model of that, you can check us out outside over here. And then don't let these images fool you. During our very first site visit, one of us have been literally fallen victim to this slope. So for another visual, here is a topographic plan view of the site. Starting from the north, up north, we have the sidewalk, which is along the streets of Yesler Way. Then we have the tree roots circled, the stone wall on the east side. And then the bottom, there is the farm entrance, fencing line, and the garden. So as we stated in the problem statement, the garden will be part of the washed off property, and anything above the fencing will be SDOT property.
So for our deliverable, we have our site plan, which consists of four big parts. Our facility map, our temporary erosion control plan, tree protection plan, and our ramp drawings.
We will also be implementing the CSI specifications as part of our deliverables. So it stands for the Construction Specifications Institute. And it's basically an easy reference document of construction details for future contractors working on this project. And we also have a copy over at our station.
We will also be doing a cost estimate, which breaks down each item that for their cost, and we'll break that down further in later on in the presentation.
Moving on to minimum requirements. So as Alana mentioned earlier, we will need a tree protection plan. So we've identified the critical root areas using the Seattle Standard Plan number 133 to identify the 3 main critical root areas. Firstly, in zone A, highlighted in red, This is the most critical area, and to be able to build here, a tree protection and vegetation protection plan will be needed. Following that, highlighted in green, this is zone B. This is a somewhat critical area, and the approval of minimum of the service plan will be needed. Lastly, outside of that is zone C. This is the least critical area, and the approval of protection plans will be needed. Overall, by identifying all these critical root areas, we will use this. We have used this to determine where to put and space our piers, which is what we'll explain now.
Thank you, Nathaniel. So, as Nathaniel noted, our site is full of those critical root zones, and we're going to be butting up really close to a couple of those trees. And so we looked at other sites and other projects that had a similar problem of foundation needing to be placed really close to trees like this. And this also happens to be a KPFF project up the shoreline, and they ended up using these diamond piers. Diamond piers are great for the applications that we're using right now, because when the diamond piers are placed, they aren't like a usual foundation system where you dig a hole and put a big block of concrete. It is a pin-driven foundation system. And that means that when the piers are being installed, the diamond piers can be angled and rotated and moved so that the pins don't hit those roots that we want to avoid and don't disturb those trees. But in order to build with diamond piers, we have to have some idea of the type of soil that we're working with. And so luckily we turned to the Washington Department of Natural Resources that collects a lot of publicly accessible soil data for sites all over the city. And while we didn't have a borehole that was publicly logged on our site, we took borehole data from sites around us and put together a couple models that estimated what sort of soil conditions we should be looking at on our site. And what we ended up concluding is that we were expecting a sand and gravel mix soil for our topsoil that the diamond piers would be placed into. And this was later confirmed when we were shown pictures of previous excavation at our site that seemed to reveal what was gravelly sand layer. And that's actually ideal and perfect for diamond piers, as that's the preferred type of soil that that diamond piers call for.
Yeah, moving on to the design consideration for stormwater. So we have, according to our stormwater code, we have to turn in something called a temporary erosion control plan. So what is a temporary erosion control plan? So it's basically a plan that stops dirt from washing away. So there's two parts to that plan. One is the narrative part, which is the written part, saying what types of tools we need to use to stop these runoff. And then we have our site drawings, which is like a map/diagram to show you where we implement these tools. So according to the stormwater code, our project is considered as a trail project. This means that we do not need an on-site stormwater management plan, and we also do not need a soil infiltration plan. And the tools that I talked about earlier is the tools that we'd be using is called pest management practice. We'll be using silk fencing, which is shown in this picture right here at the bottom of our site, and temporary fencing. So moving on to design for the ramp, and we have to design our ramp according to ADA guidelines. So we have to design our ramp to make it accessible for everyone. This includes a 112 slope and handrail on both sides, and then a 60-inch of level landing, 60 inches of rise should have a level landing, and the level landing should be 60-inch by 60.
Based on what Alana said about the standards, our team came up with a couple of iterations for ramp paths, and ultimately we chose this ramp path starting from the left side of the sidewalk, sloping down to the farm entrance. Now, some considerations we had were the ADA compliance of a 8.33 maximum grade, which is also known as the 1-12 slope, and also following the minimum landing width of 60 inches by 60 inches. And one more thing, as Daniel mentioned earlier with the critical root zones, we're trying to avoid any of the tree roots to sustain, to promote sustainability.
All right. So moving on to our design process. Before we move on, I want to point out this long section that was part of our design process and part of the path that we chose was that we wanted to avoid putting piers next to that tree. And that'll come into play when we talk about the design process of the structure. So here's a cross-sectional view of our ramp, and there's a lot going on here, but we can see the components that make up the ramp here. We use 6x6s, 4x4s, 4x6s, all pressure treated sawn lumber to make up the components of the ramp. The 6x6s are these large components, the beam and the pillars that hold a lot of the weight and forces of the ramp. And the 4x4s make up the components that run along the length of the ramp, such as the joists and the handrails. Additionally, we make sure to include aluminum ramp treads on the surface of our decking to ensure a non-slip surface, which is part of our accessibility goals. And we also use Simpson Strong Tie connections to keep our wooden members together. And so the idea behind the loading path of this structure is that clearly most of the decking, most of the loading goes in through the decking, and that is where people walk, where we're going to be expecting most of the live loading. That gets transferred down into our joists. And also a lot of lateral and vertical loading is seen through the handrails. And both the deckings and the handrails loads are passed into the beam that hold both of them up, down through the pillars that are holding the beam, into our diamond piers, and finally into the ground.
So when we had to do all these drawings, we came up with this one of the first ones we did was this joist, girder, and girder layout. You can see here the girders running lengthwise, the joists, or the girders, I'm sorry, these short ones, the joists are running lengthwise, and then the blocking in between. After we took this, we did these, notice that there's these 5 different landings. These landings are important because with ADA standards, you have to have a landing whenever it turns, or the rise, as we had talked about before. Then we broke this down into 3 different sections. This top section is where the concrete meets the sidewalk, or the ramp meets the sidewalk. Notice here we needed to have a very level landing. This is important as we want to make sure that there's smooth transitions with trips. Next, we broke it down into the second section. Okay, this section, you notice there's cross bracing. This is where we want to make sure those loads, those lateral loads are there. And also notice the diamond piers and the ground surface as well again on this one. Then this long section, I had to break down in 2 different sections. Sorry, technical difficulties.
I got it.
Okay. Then we broke this down, the longer section. Then if you notice the bottom section, we have 2 diamond piers at the very end here. These need to be dug out. This is okay with diamond piers as long as we backfill with gravel so they can be maintained in the future.
Yeah, I also wanted to point out the diamond piers that we use for this long section that we pointed out earlier have a higher bearing capacity because it is a longer unsupported section, and that leads us into our demand stresses. So in order to make sure that our structure was structurally sound, we took our designs and made a 1-to-1 scale 3D model of our ramp in SAP 2000, which is a structural analysis modeling software. And we applied the loads that we need to be designing for according to the Seattle Building Code, which was 60 pounds per square foot on the decking and 50 pounds per linear foot along the handrails. And what the SAP model helped us do is it output the stresses that each member is expecting to see. And we went through and input all of these into an Excel sheet that went member by member, and also took the demand capacity that we now know from our SAP model, and we had to find our stress capacity. In order to find stress capacities for our timber members, we consulted the American Wood Council's National Design Specifications, and that lays out the process for outlining how it is that each member is being used, and the length of it, and the environment that it's being used in, and that gives us a stress capacity for that specific member. We automated this process using an Excel sheet for all 650 something members, and we compared the demand stresses from our SAP model to the capacity stresses from the American Wood Council's NDS, and we got a super long 600 something long Excel sheet, and we made a summary sheet which summarizes the highest DCRs that our members see. And a couple of these were expected, a couple were unexpected. This 2.3 demand capacity ratio is part of that really long unsupported section. We expected this and expected that to fail and be out of our scope. However, the model also gave us these outrageously high DCRs for our railings. And that was also seen, we determined that to be a modeling issue, and that was determined to be outside of the scope due to time constraints mainly.
So lastly, we took this all and we put it into a cost estimate, breaking down each of the different line items and how much they would cost as an estimate with labor. We came up with a total factor, with waste factor, or otherwise known as a consolidation factor, that is of 35,000. And then we took all of these different deliverables and we put them all into our report. And we're gonna give these to KPFF and the Black Farmers Collective, and they will then move forward with the project and hopefully build it. Any questions?
Thank you. Thank you all for your patience and for letting us fire those information at you. It was a pretty big project, a pretty big scope. So yeah, any questions?
With all the standards and specifications that you have to work with on your project, do you have any opportunity to be innovative?
One of the things with KPF or with okay, so the question was, we could be innovative on our project. Okay, so one of the things when we were talking to the Black Farmers Collective is they wanted to try and keep it aesthetic. So we kind of stuck with wood as it was a better aesthetic. We did look at other options, but it was one of the things that aligned with our project. So that's one of the reasons why we stuck with that. The thing that we did figure out, we knew was those diamond piers, those were new to all of us. So that was kind of our innovation. We didn't know about diamond piers before this project.
Yeah, I mean, it's kind of hard to not have to innovate when you're stuck with a site that presents a lot of challenges like that. Because we have that section where we get really close to the trees. So there was a lot of innovation that needed to be done to figure out what type of foundation systems we're using, to figure out the sort of connections we're using, and how we are expecting that long section to perform. And additionally, the SAT model is also a big part of our innovation process, because the loading conditions that we were expecting were just really, really complicated to try and map out those reactions across the entire structure. And so it was nice to be able to use that as a method of collecting our stress demands.
If you were to move on to 60% design, what changes or adjustments would you make?
Do you want to start, Patrick?
That's a hard one. I'm not exactly positive. This is something that I'd probably work with KPFF to figure out exactly 60%. I'm guessing it would be lots more detailed drawings of each connection and things like that nature, as well as maybe a site investigation of the soil with a site surveyor, to do all the soil analysis. I think that would be part of it, and then there's probably a few other little things I'm missing.
Yeah, I mean, there's the project, we initially entered it expecting to be mostly designing the structure, and it ended up being mostly figuring out our permitting requirements for stormwater management and our soil analysis. And I think that the first thing that I would do if I had more time on this project is would be tackling those structural demand capacity ratios that we're failing, especially that really long section. We don't have the resources to figure out exactly a solution to supporting that long section. I think that would need more consultation from professionals that can go on the site and analyze exactly where it is that we can place an additional pier. And so I think that would be the first step that we would take.
What's that question?
So you mentioned the trees on this site. Is the trees like continuing to grow and those roots continuing to grow something that you factored into your design? Like, could that potentially affect your design in the future?
Yeah, to repeat the question, is the continuation of the trees roots impact our design? To answer that, I'd say no, because like the longevity of our project is still varying. We don't know how long the rent will be on our site. It could be 20, it could be 5 years. So we don't really take that into account in our design.
The ramp was based on some access issues related to handicap or whatever. Once they make it into the garden or that area, is it a flat area? Is it okay for that
Yeah, I love talking about this. So, no, it is not a flat area. This is one small part of what is a bigger project to make the entire farm a lot more accessible. And so you'll notice on a couple of our slides, we have at the end of our slide, at the end of our ramp, there is a big concrete circle. And that would be the ideal landing area. We didn't have time to be able to design that. But that is another part of the design of the accessibility process. And we're honored to be able to complete this first part, this introduction into the farm and to making it accessible. Because it's really important for folks to have access to spaces like this, especially folks that live in the area that want to be able to access the farm more, but can't because they're scared of falling like I did. But yeah, no, there's still a lot of work to be done even after this net is built. Yes.
You mentioned that this parcel outside the fence is owned by SDOT. What sort of permitting requirements do you have with SDOT, and did you actually speak to SDOT about building something on their property?
So the question was, the land is separated into, is owned by two entities. So do we look into any permitting requirement on SDOT? The thing is, right after the fence, we didn't look beyond that. So, because it's such a funky area, I think it will move on to KPFF where either they have to talk to someone at SDOT or maybe they need to go to a special requirement for that project. But
there needs to be additional survey.
yeah, there also need to be additional survey to actually define clearly what the right is.
So I was just curious with the diamond foundations, are you guys have any insight on how those are installed? Are the pins driven one at a time, is the whole system driven at the same time?
So from our little research that we've done, they're very small, little 2 by 2 foot square that fits the main head. Then they are driven in, either using special tools provided by Diamond Pier, or we've also heard that they've been used just by sledgehammers and slamming them in. I don't know how exactly perfect that would be. And then they are installed as you go. We would lay them all out most likely, and then plug and place them, and then dig where they need to be, and then make sure they're not hitting the tree roots and so on and so forth.
Yeah, so here's a little picture of the diamond pier. The diamond pier, the concrete block is placed, the little nexus is dug out for its place, and then the pins are driven with this special tool, which is an excuse for Diamond Pier to charge you to rent their special tool. Yeah, I mean, they're literally just driven in, which is great for us because it prevents excavating in that huge area. We can just drive the pins in. And that's part of the challenges that we mentioned earlier about needing to know where we can and can't drive the pins.
And to add on to that, as mentioned earlier, we have the CSI specification. There's going to be a section just for the diamond pier, so there'll be a couple of like procedures or requirements or materials needed added onto that.
Thank you. Project is sponsored by
What the CID is a fairly new sponsor. This is the second project that we have completed. So I'd like to thank the board for supporting us in our program. So with that, I'll give it over to the.
At the bottom of the dash.
Okay. Hi, welcome in guys. We're TCE 25.4 and we're doing the environmental remediation of PFAS at the Seattle-Tacoma Airport. I'm Livy. I'm Audrey. I'm Tana.
And I'm Sam.
Okay, wow, there's a technological difficulties. So the outline of our project is we're gonna go through the background and then we're gonna go through the preliminary technology selection. We're gonna go through our 10%, 30% design, and then we'll have questions. So a little bit of our project organization, we have our lovely sponsor, Port of Seattle. We love them, thank you guys very much. Megan and David Weish, and then we have Dr. Mike as our faculty advisor, and then our coordinator is Dr. G. So project overview. So the problem we're having at the airport is that there's contamination in the aquifers at the Seattle-Tacoma Airport. This contaminant is PFAS. The priorities we have is we want to minimize risk and exposure and prevent that from spreading. And then in addition, the task we have to do is estimate the extent of that plume or that contamination, and then select remediation technology, and then design that technology to 30%. So PFAS. What is PFAS? PFAS are per and polyfluoroalkyl substances. It took me a while to learn how to say it. They're hazardous to humans, animals, and the environment. They cause immune disruption. There's linked to kidney cancer, liver cancer. There's lots of links to lots of different issues. So we're going to try to remediate that. It's in lots of different things. It's in your nonstick pans, your clothes, firefighting foam, and the problem with this is it's known as a forever chemical and has a carbon fluorine bond, which is the hardest to disrupt in nature. So the technology we're trying to remediate is going to break this bond. Site history. So we're at the Seattle-Tacoma Airport, and in the Seattle-Tacoma Airport, there's been routine cleanups. So the fire department has been doing those cleanups for 20 years for 5 gallons a week of accumulation. This is the discharge site, and in this discharge site, it has caused 95 feet deep of contamination. The site constraints we have is when doing this remediation project, we have to think about there's going to be airplanes going. In addition, the support of Seattle has to be able to get to the different fires, and there's lots of utilities in place.
The proximity to the runway means that there's a 30-foot height constraint on any construction equipment that we would need to bring on site. In addition, this image shows the complex network of utilities surrounding our site. This is important to consider because during our design, we can't drill between 5 to 10 feet of utilities and powered lines.
So our team evaluated 7 different remedial technologies, including granular activated carbon or GAC, ion exchange resin or IEX, foam fractionation, thermal treatment, electrochemical treatment, the removal of contaminated soil, and colloidal activated carbon or CAC injection. Of those 7 technologies, the first 6 are ex situ treatments, which means that the groundwater is taken out of the ground and treated and either disposed of or reinjected. For the purpose of our project, we assume reinjection. And CAC is a in situ remedial alternative, meaning that the groundwater is treated in place in the ground. So you can imagine that 7 technologies is quite a lot to evaluate in just 9 months. So the Port of Seattle advised us to make a preliminary selection matrix in order to narrow it down from 7 technologies to 3 technologies to evaluate a 10% design, and then ultimately one of those to 30% design. In order to do that, we used a disproportionate cost analysis or DCA ranking criteria from the Washington State Ecology Feasibility Checklist. There are 7 criteria in that checklist. However, the court asked us to look into 3 specifically, which were protectiveness, which covers human health and the environment, implementation, which covers our technical and administrative feasibility and cost. However, for the preliminary matrix, we did not cover cost because we looked into that later on in our 30% design matrix. So in our matrix, we used the two criteria and we made two subcategories for each one. And then we ranked all of these on a score of 1 to 4, and then averaged those scores for a total score where a higher number means a more favorable result. That left us with 4 top scoring remedial alternatives instead of 3. However, from those site constraints that were mentioned earlier, we know that the removal of contaminated soil is not a practical solution for our site. So once we removed that from the list, we were left with granular activated carbon, ion exchange resin, and colloidal activated carbon injection.
So we began by doing a preliminary 2D model, and this is the estimated extent of that contamination. We were given 4 monitoring wells, which is monitoring the contamination at those, the contamination concentration. And we're focusing on 4 different types of PFAS. These are the ones that are most regulated and most known. The numbers in red recognize the contaminations that are above the state action limits, so that's what we're going to target. Monitoring well 2 is where that discharge site was happening, so we used monitoring well 2 and the Doug Fox well to model a 2D plume. And this is the one for PFOS, which has the smallest plume. This is about 500 feet of the 1,000 feet. The red lining is the ones that are above state action limits. And then we have PFOA, which is goes past the Doug Fox monitoring well, which will be the main one we're focusing on since this one had the most contamination spread. The problem with this plume though is this does not show any contamination at monitoring well 1, and monitoring well 1 we do know has contamination, but we are using this to continue making a selection process.
So we use a 2D model to inform our 10% design calculations. And just to give you a reminder, both GAC and IEX are ex situ treatments. Specifically, they are pump and treat treatments, which means that the groundwater will be pumped out and into a contactor filled with a specific media. In this case, granular activated carbon or a strong base anion resin, specially formulated for PFAS compounds. The colloidal activated carbon is an in situ treatment. So in this case, we would be injecting colloidal activated carbon directly into the groundwater. So we calculated our carbon utilization rate, which gave us a 7-month change between media, and that equates to about 7 tons of carbon per year needed. For IEX, we used a linear adsorption assumption, which gave us about a 14-month media change interval, and that equates to about 5 tons of resin needed per year. And for CAC, we used a down gradient plume capture, and from literature values of similar projects, we think that it'll be about 30 years before reinjection would be needed, if reinjection is needed at all. And our 2D model gave us a barrier length of about 250 feet needed. So then we looked at our 10% design costs, where we researched using literature values from similarly sized projects, and we took an average of those numbers and applied it to our project. So for GAC, we came in at about $18 million. For IEX, we came in at about 10, and for CAC, we came in at $1 million. We recognize that $1 million is quite low and not a realistic number. However, we are very confident that it would be the lowest cost of the 3 designs. We then added a contingency to each design. So for the 2 pump and treat options, we've added a 40% contingency for pumping rate variability. And for the CAC option, we've added a 20% contingency. We mostly use the Federal Remediation Technology Roundtable, or FRTR, but we use some other literature values as well. So in our design matrix, it looks pretty similar to the preliminary selection matrix. However, we've added 2 extra subcategories to each criteria. So for protectiveness, we've added the longevity of treatment, and for implementation, we've added the risk to underground infrastructure. We've also added in our 10% design costs and our sponsor priorities. We then again ranked each technology and then took an average score for a total score, and we found that CAC was the winner.
After selecting CAC as our preferred remedial alternative, we moved into our 30% design phase. In this phase, our 4 major deliverables were a 3D model sensitivity analysis, creating a barrier field layout for CAC injections, developing a future monitoring plan, and also providing a project cost estimate.
For our 30% design, we wanted a more accurate representation of our contaminant plumes, so we used MT3D and ModFlow 6 in the graphical interface model muse to create an advection and dispersion model. The purpose of this model was to generate a more accurate plume width to do temporal modeling, which predicts how the plume moves over time, and finally to determine the extent that the contaminants are above the state action limits, all of which helps inform the amount of injection wells and their location. We ran into a similar issue when calibrating this model as we did with the 2D model. The single source at Mining Well 2 did not generate a plume that encapsulated the known concentrations at Mining Well 1. So we looked at more data sent to us from the port and found that all 4 of the PFAS molecules were measured and had measured concentrations in the Vado zone at Mining Well 1, which confirms there's discharge at this location as well and justified us adding a second smaller station during the model. To calibrate the model, we adjusted the amount of time it ran for. We know the discharge took place for roughly 20 years. It's been 20 years since then, but we don't have an estimate of how long it took for the contaminants to get from the surface, 95 feet down to the groundwater table. So we slowly adjusted the time going up from 1 year until 17 years where the concentrations at all the wells lined up. Here's the temporal model for PFOA running for 5 years, 10 years, 15 years, and finally 17 years when all the concentrations in the model of the mining wells lined up in the observed range of values. After calibration, we conducted sensitivity analysis, and this is to determine what parameters, when changed, have the biggest impact on the model. To do this, we measured in the model the distance from mining well 2 to the state action level after adjusting a key parameter by plus or minus 25%, and compared this to the default model, where this distance was 602 feet. In doing analysis of the results, we found that the coefficient of dispersivity, which impacts how the soil interacts with the contaminant, and the hydraulic conductivity, which impacts how quickly water moves through the ground, had the highest impact on the model results.
The priority of our design is to contain areas that exceed state action levels. To do this, we integrated our 3D plume model with GIS to create a plume map where areas exceeding state action level are highlighted in red. We use this map of PFOA concentration specifically as it is the compound that has the largest area exceeding state action levels. At our small plume, the width was about 100 feet, while at the large plume, we found the width to be 330 feet. As a refresher, CIC is an in-situ technology, meaning it treats groundwater within the soil. At our site specifically, we use CIC technology to contain the spread of PFAS. A permeable reactive barrier is formed by tight rows of colloidal activated carbon injections. These adsorb PFAS as the groundwater moves through it, preventing further migration off-site. At our site, these barriers will be installed down gradient of the plume's exceeding state action level to prevent further migration. This image here shows the barrier field layout at the large plume, where CIC injection points are highlighted by the red squares. Each point has a 5-foot effective radius and is designed not to interfere with any buried underground utilities. Each point is placed in staggered double rows, forming a 13-foot width barrier for the PFAS to interact with as it moves through the groundwater. At the large plume, this requires 132 injection points, while at the small plume, this requires 40 injection points. In addition to just planning the CIC injection field layout, we also developed a future monitoring plan where we place monitoring wells to measure the effectiveness of our treatment over time. This requires the installation of monitoring wells placed before, inside, and after reacting with our barrier. While determining our final project cost estimates, we factored in capital consulting costs, which are broken into product and application costs, as well as monitoring costs, which include laboratory and consultant costs. The design assumptions that we used to calculate this final cost value were a total barrier length of 430 feet between the two barriers. This requires a little over 160,000 pounds of injected carbon, and this takes place over a treatment period of 15 years, where 8 monitoring wells are required and measured twice per year. After adding a 30% contingency to our final cost, we ended up with a net present value of $3.9 million. Thank you for listening.
Great work, and a really important problem. I know that granular activated carbon works for a lot of different pollutants, and I'm wondering, Is there any analysis of the groundwater to show that PFAS is the only contaminant of concern, or are you going to, are other pollutants going to be competing for the sites on the granular activated carbon?
So at the site, the main source of our contamination just comes from firefighting foam. So those are the only contaminants of concern that we're taking a look at. And those are the only ones that we expect to be competing as it goes through the groundwater.
Do you know if there's been monitoring for other pollutants within the groundwater?
As far as I know, they're not monitoring, I'm not 100% sure, but I do know that there are other competing organic compounds, and those are in the cost estimations at the very least.
I have a question about your modeling. So you used MT3D and Mockflow 6 models?
Yeah, so the question was whether we used MT3D and Mockflow 6 to model, and yeah, we did use both.
Were they like separate or do they work together?
They work together. The MT3D is specifically for contaminant transport, and Modflow 6 is just generally like the hydraulic model. So the water, how the like groundwater table moves over time, and then the MT3D is how the contaminant moves through.
Oh, I see. One more question. Were those both free models or did you have to pay for them?
Say that again, please.
Are they like free, publicly available models?
Yeah, they're free. You can download them. They're made by USGS, United States Geological Service. It sounds for something like that. You can just.
Do they have to relocate any utilities, pull off that tank that you guys are showing?
At this one, we actually were fortunate enough not to have to relocate. Some of the power lines might need to be, but we do need to, for some of the pipes, we do need to excavate it, so we make sure, for the shallow pipes that we can see where they are, so we don't drill like close into them. We can't just go into it without digging them up, for some of the ones that are tight, but we don't have to move anything around.
That was also part of like the, when we were analyzing the different technologies, is looking in, that's a big part of the problem there. So we're looking at technologies, we definitely took a big step in looking at.
So I think you said that you would be doing it for 15 years. After that 15 years, you'd be expected that we wouldn't have any, it would have taken care of all the PFAS, or?
No, well, it's a contamination we're trying to prevent the spread of, so it doesn't get into like water sources, like there's a local lake nearby and things of that sort. The problem again is like all the utilities and things, so as long as it's within the, like it stays in place, it doesn't pose a threat to anything. So no, it won't be removed, it'll just be contained.
The treatment period of 15 years that we used in our cost estimate. Okay, sorry. That number is before reinjection might be needed, just so there's no breakthrough in the barrier. But like we said, it's not being removed. That's just to prevent it from spreading any further.
How, is there documentation how long the PFAS can be absorbed with the carbon you injected into the ground? Would that after, is there any documentation after X years, would that start leaching PFAS out of that again?
So other literature reviews, they tend to be about 30 years. These are all kind of new technologies, so we don't have an exact number. So we factored of safety back down to 15, factor of safety of 2 there. But that's why we also provided like a monitoring plan, so we can see if there's any breakthroughs before or after.
We take one last question from Tamara.
Sure. I had a question similar to the technology underground utilities being disrupted. How exactly do you inject the CAC into the ground?
I'm sorry, could you repeat that? I couldn't hear from here.
How do you inject the CAC into the ground?
Yeah, so the question was with all the utilities, how do we inject CAC into the ground? Other projects usually use direct push rigs. Since our contamination is so far deep into the soil, we would probably be using sonic or auger drills to get in there. So it's just a big drills, yeah. Thank you.
I know, I'm gonna think about it, man. I'm standing there, it's like, what? Yeah. No, well, I think there's other stairs. So there's some projects that is on the pivot, and they don't want to go on a project, that makes it work. And bring them to the couch. Yeah, see me out there when we go, okay? So you know,
Yes, okay. So our last project is an environmental science project sponsored by Keta Legacy. And Keta Legacy, this is the first project that they have sponsored, so I'd like to welcome them to our family of sponsors. So with that, over to the team.
Hello, everyone, and welcome. I'm Sanhita.
I'm Laurel.
And I'm Alec.
And we are Environmental Science Team 25.1. This year, we were sponsored by Keta Legacy Foundation, and our project is centered around riparian ecosystem management at the Rhododendron Preserve. While we're here, we'll be going over our background, methods, results, conclusions, and acknowledgements, and we'll have some time for questions at the end. Before we get into anything else, we have our project team organization here, where our Keta Legacy Foundation sponsor liaisons were Linda, Eva, Casey, Mandy, Amy, and Jeff. Our Seattle U faculty include both Dr. G's, and finally we have our team.
The Keta Legacy Foundation was originally established in 1968 as the Mountaineers Foundation, a nonprofit organization based out of Kitsap County, Washington. And their main goals are centered around environmental conservation, stewardship, education, and the protection of areas like the Rhododendron Preserve, which is our area of study, an area of roughly 500 acres of protected land that's owned and managed by the KLF. So their mission is to inspire community involvement and stewardship through conservation efforts, education, and important scientific research. So this area, shown in green, the Rhododendron Preserve, is part of the Puget, one of the largest remaining old growth forests in the Puget Sound. It's also part of the Chico Creek watershed, shown in black. This area is home to a large variety of vital salmon spawning habitat and one of the largest chum salmon runs in the area. And this place is of high importance for environmental studies, as lots of areas within the preserve have remained largely untouched throughout history, allowing for lots of studies to be done on riparian ecosystem health, biodiversity, and the effects of climate change over time.
So to go a bit more into this, a riparian ecosystem is essentially a transition between an aquatic and terrestrial ecosystem. These are very important as they help with things like supporting biodiversity, regulating nutrient cycles, and even water quality. Adjacent to these is the stream spawning habitats, which is where salmon lay their eggs, making these very important for things like supporting the salmon populations within the Puget Sound. Additionally, some species die after they spawn, and their body decomposition can release nutrients into the system, which can then be taken up into the aquatic and riparian ecosystems. So to break this down a little bit further, when salmon spawn, they go from their live form seen on the top here to their dead and decomposed form. This can then release nutrients, which is primarily seen in the forms of nitrogen, phosphorus, and potassium. This can then increase the nutrients to the surrounding area, which either stays in the stream or gets taken up to other ecosystems via consumption, chemical uptake, or wildlife transfer. The primary of interest here was the terrestrial one, where nutrients can leach into the soil via the water table, which is the boundary between the saturated and unsaturated soil seen in the diagram here.
This can then be taken up by plants due to their ability to reach their roots into the water table and take up water. This is then beneficial to plants, where nitrogen promotes stem and leaf development, phosphorus root development, and potassium supports with water regulation, which can then help other nutrients being taken up. This is then beneficial to the ecosystem because it can promote things such as carbon sequestration, erosion control, and even the creation of canopy cover, which goes into protecting our salmon habitats. So we want to ask the question within our preserve of how do water and soil nutrients interact within spawning ecosystems? Within this, we expect that an increase in water nutrients will lead to an increase in soil nutrients, which will then benefit plant growth and abundances.
All right, now that we have gone over our research question, we'll go over the methods that we use to try to answer it. In the field, we selected 6 up and downstream locations along Lost, Wildcat, and Chico Creeks, shown in the map here. And the code system that we use to refer to these sites is shown on the right, where the first letter indicates which stream and the second letter indicates up or downstream position. We selected these sites so that we might be able to see any spatial variations within the preserve. At each site, we selected 30-meter transects on either side of the stream along which we collected our data. Water samples were collected from the center of the stream, while soil and plant data were collected every 10 meters along the transects. At each sampling point, we created 2x2 meter quadrants at which we collected our vegetation data. We recorded the species present as well as the abundance of each. For soil metrics, we measured temperature and pH using the probe shown in the middle, as well as soil horizons shown on the right. This basically shows differences in soil composition. We recorded the organic layer, which is the uppermost layer and composed mostly of leaf litter and other organic material, as well as the A layer, which is the layer of topsoil found directly beneath. And finally, we took back some samples for nutrient testing that we sent to MySoil, which is a professional soil testing company. We collected one additional soil sample from about 6 inches beneath a decomposed salmon carcass for later reference. And this salmon carcass that we sampled was found really close to our Chico upstream site.
All right, and then in a similar fashion to the soil data, we also collected temperature and pH data for the water. This is to make comparisons between the site and adjacent transects. We also collected velocity, dissolved oxygen, and turbidity data. These latter 3 being of importance as the velocity helps us determine the size and extent of sediment movement within the streams. Dissolved oxygen is a good metric for determining the viability of those streams for salmon populations. And then turbidity is the suspended solids within that water. Now I'll go into a little bit more depth on the nutrient testing we conducted at the lab. So we used Hawk spectrophotometric measurement kits, which come with pre-dosed vials of reagents. They're then subjected to an incubation period and go through chemical digestion. And after that, we're able to use them to determine our nitrogen and phosphorus concentrations.
So moving on to our results, just a reminder, the question that we wanted to answer was how do soil and water nutrients interact within spawning ecosystems? So before I actually go into depth of this, just as an overview, whenever we plot things against our different sites, we broke this down into 2 different categories where the differences in stream are indicated by colors and the differences in stream position of upstream and downstream is indicated by the differences in patterns. So to answer our research question, the first question that we asked was, does the presence of a fish carcass affect the actual soil around it? And within this, we plotted the different nutrients of total nitrogen, phosphorus, and potassium against the different sites compared to our fish carcass site, which is seen in the red dot with a dashed line. Within this, we see that the total nitrogen is highly elevated. In fact, our fish carcass site falls about 27 times higher than the average of all the other sites. Next, with potassium, we see that potassium is only slightly elevated. It's above most of our sites, except for our Chico upstream site, which is indicated in the kind of like yellow without the pattern. This is likely due, like we mentioned earlier, due to the fact that these are very close to each other. The reason why we think we're seeing this data is first within total nitrogen. The salmon carcass proteins contain a lot of nitrogen, and given that the carcass is about 15 to 20% protein, you're naturally going to be seeing a lot of nutrient depositions in the form of nitrogen. Next, within potassium, potassium has the ability to bind to soil particles, particularly clay, making them harder to test accurately. Next with phosphorus, phosphorus seen here is actually not elevated as it falls within line with a lot of the bars that we see here. And this is likely due to the fact that it's contained in the bones of the salmon carcass, which take a lot longer to release their nutrients.
Right, now that we have seen and confirmed that salmon carcass presence does impact the soil around it, we wanted to investigate how these nutrients might vary with proximity to the stream, since that's the source of those carcasses. Here we plotted the concentration of potassium along our transects at each of our points, and the same code system is used to refer to each of these points. The lighter colored dots indicate lower potassium concentrations, while darker colored dots indicate higher concentrations. The general trend seen here is that as distance from the stream increases, the concentration of potassium decreases. This trend was really closely followed by two of our sites, which were the left transect of our lost downstream site and the right transect of our wildcat downstream site. This is a little bit more simply represented here, where only those two sites are plotted, with the lost site in teal and the wildcat site in purple. This trend indicates a possible link between stream-derived nutrients from salmon carcasses and soil potassium concentration. This could be due to groundwater's ability to transport water away from the stream, which would account for there being a higher concentration of potassium closer to the stream than farther away. And now that we have seen a couple of factors that can influence the concentration of nutrients in the soil, we wanted to explore how these nutrients can then go on to impact their environment. So here we plotted vegetation abundance per sampling quadrant against the nutrient concentrations for total nitrogen, phosphorus, and potassium. Total nitrogen and phosphorus show low correlations in the data, while potassium exhibits a significant positive correlation. One explanation for this could be that total nitrogen and phosphorus are not limiting in the system, while potassium is, which would make potassium a more important driver of vegetation growth and abundance here. Additionally, different nutrients have varying lifespans within the soil. For example, nitrogen-based compounds tend to be more readily available for plant uptake. Potassium's role in plant water regulation could also play a role here, as that can go on to benefit the uptake of other nutrients. The last thing we wanted to consider was the timing of our sample collection. We collected this data in late winter, while the majority of plant growth occurs in spring and summer. So it's likely that the data that we see here might be more reflective of plant growth trends for the coming season rather than what we observed in the field.
All right, now I'll go into a little bit of depth of another potential nutrient input through litter accumulation or O-layer depth. As we can see on the right-hand side, there is largely positive, strong correlations with distance from the stream and accumulation of litter. We attribute this to the fact that the left-hand sides of the stream tended to have much greater slopes. And so as we're moving further away from the stream, we're moving further away from the water table and reducing its disturbance with those locations. On the right-hand side, we saw more inconsistent results, with only one showing a positive, strong correlation, while the rest are either weak or inconsistent. And overall from this, what we expect to see is greater O-layer accumulation as we move further from the stream. Given that the vegetation density was also increasing, there's reduced disturbance as we move further away from the water table. And this could all be varied though based on bank-specific and site-specific factors.
So moving on to our conclusion, what we found within our study is that the presence of salmon carcasses do have the ability to elevate select nutrients. While this is the case, it held less of a spatial correlation than we originally thought, meaning that these nutrients might be less mobile than originally expected. Although they're less mobile, they still have the ability to affect the vegetation community, where an increase in potassium concentration was correlated with an increase in vegetation abundance. Lastly, while the salmon spawning as a nutrient input is very important, it might not be the only factor within our system, and so we need to consider other factors such as the organic layer.
All right, and finally, we have a few recommendations for any future studies that we conducted in this area. The first being to increase monitoring frequency to fill in any temporal gaps we might have missed, so summer and then late spring months. We'd also like to see an expanded hydrological analysis to include water table data as well as topographic mapping. Then to conduct a marine isotope analysis, and what this would do is it would allow us to determine whether or not those increased nutrient concentrations within the soil are actually derived from the salmon that are spawning there. And then finally, we'd like to see a refined soil testing procedure as well as lab work.
Finally, we'd like to once again thank everyone who made this project possible. Big thank you to our Keta Legacy Foundation sponsor liaisons, especially Linda and Eva. Thank you for being here today. And thanks again to our Seattle faculty and the Project Center. Woo!
The audience.
Graph of determining the concentration of phosphorus and comparing that to the distance from the stream. And one of them, in the top right one, the phosphorus concentration is still pretty high. And distance from the stream in the Chico upstream, they're putting it into that.
That's the location that's nearest to that salmon carcass that we found, that we did our soil measurements on. So we attribute these higher levels to the proximity of salmon carcasses that we found.
Additionally, within this Chico upstream site falls pretty high above the water table. There's probably at least a 15-foot drop between the site and then the actual river level. So I wouldn't be surprised if this is due to that. And then additionally, this is where the homestead originally was. So I also wouldn't be surprised if there was other contributing factors due to the fact that there was a homestead on this property until about the 2000s.
Thank you to the.
As a group, try to look into how many, what's in that particular year that you sample, how many salmon ran through the stream, and trying to correlate salmon run to your nutrient concentration.
Yeah, so for just repeating, it's in terms of our study and then in comparison to the amount of salmon that were coming in. This was actually a record number that of the salmon coming in. We were out there and we were lucky to be out there when the salmon were running. It was absolutely beautiful. But there is a partnership between Keta Legacy Foundation and then some of the local tribes, and the tribes walk the stream and count how many salmon are walking through there. So there is that data accessible to us. We just didn't have the time to actually go into that data.
I think the run this year was 65,000 chunk.
Within the Chico watershed, not just this area.
Thank you. Session, and we have one more environmental science activity that we are doing at school. So that will be the
So good afternoon, everyone. Welcome to Project Day, and thank you for all joining us today with us. And it's great to see online and also the in person. And I'm Wan Bei, I'm faculty in computer science, and I will be a moderator of this session. And today, each team will present their project for 50 minutes, followed by 5 minutes for the Q&A session. So the audience, please hold your question until the team finishes their presentation, and we're gonna take 2 or 3 questions. The team, and please make sure that you are on track. I'll give you some signal to 2 minutes prior to the 15 minutes, and I will give you another sign for the time. So first, team will be drone-based data collection and interpretation of forest structural conditions.
Hello, everybody. We are the Interdisciplinary Team 25.1.
My name is AJ. These are my lovely teammates, Jeremy, Miranda, Emily, Emma, and Ben. On our project, we're going to be giving you talking about the drone-based data collection and interpretation of forest structural conditions. Yep. So here's a basic background of our presentation today. We'll start with some background. We have been working with Resilient Forestry with our project liaisons being Miles Lefebvre, Russell Kramer, and Brian Fuentes. Our faculty advisors are Dr. Bay, Dr. T, and Dr. Lauer, with our design coordinator being Dr. G.
Our sponsor, Resilient Forestry, is a forest consulting company that provides forest inventory services using ground-based data collection and drone surveys. And this can be done with LiDAR, which is the process of putting lasers into the canopy or the ground, and it returns accurate elevation data. But Resilient Forestry uses structure for motion, or SFM, which takes 2D images, stitches them together, and creates 3D models. And we'll explain this process further in our next slides.
So one of the core components of our analysis is the point cloud. A point cloud is a 3D representation of our surveyed area in which we utilize the collected drone-based imagery and stitch them together and then shoot a whole bunch of dots basically at this to give us a high accuracy vector-based model of our forest.
Some applications of the forest inventory services that Resilient Forestry provides are biomass estimations, which are helpful for carbon sequestration and timber yield estimations. Additionally, fire risk assessments, as these are becoming even more prevalent in Washington State as our periods of drought are becoming even more prolonged. And most importantly, the overall resilience of the forest.
Based on this, we designed two main project questions. What are the optimal flight parameters to create the most efficient and accurate models? And can we derive valid data from our methods? For our project, we used a test site, which was Lansford Park. Lansford Park is a 31-acre forest in Maple Valley, Washington, and it has an extensive plot network that's maintained by King County. Additionally, it is comprised of densely packed Douglas fir and is impacted by laminated root rot, which is a native fungus that spreads between contact between infected trees. Our project began with data collection using ground-based data collected by King County in their plot surveys, as well as aerial-based data collection collected via a series of different drone surveys using different combinations of flight parameters. Next, we attempted to automate steps in our process so that the user can upload a series of 2D images, generate models such as canopy height and tree approximate object models, and then extract relevant ecological metrics in a time-efficient manner. Finally, we performed accuracy and efficiency analyses to determine the overall accuracy of our models using the different flight parameters. Additionally, we used derived and ground-based metrics and did a comparison using metrics such as basal area, diameter at rest height, and biomass to determine the overall accuracy of aerial-based surveys.
Moving on to modeling, the first step before we flew the drone was to set ground control points, or GCPs, and these are physical markers that need to be seen by the drone while it's in flight. And we placed these throughout the forest and along its perimeter. And once we placed these, we took the coordinates using a high quality GPS. We used a real-time kinematic, or RTK GPS for this. And once we had these coordinates, we were able to input them into the software we used in order to ensure that our LiDAR-based digital terrain model and our surface-based, or sorry, our digital surface model, were correctly aligned. The next step before we flew the drone, and the last step, was to create our flight plans as seen on the right. And the drone flew on these blue lines, capturing images about every 2 seconds. And for our answering our first question of what are the ideal flight parameters, we tested between 2 different flight parameters, those being image altitude and image overlap, For altitude, we tested between 300 feet versus 400 feet, and for image overlap, we tested between 70% versus 90%. We kept our drone speed at 11 miles per hour and our capture angle at -70 degrees. And there are many different combinations of these parameters that can be used. However, we use these based on our literature review and after looking at King County's based ground data.
So in order to automate our analysis, we developed a 3-stage pipeline in which we intake our aerial image set, and then we pre-process this, basically removing blur as well as noise to make the images a little bit more sharp. And then we reduced the resolution as well, just to make sure we have a standardized format in which we utilize in our next stage of the 3D point cloud generation. We utilize the WebODM software for this, and this creates our point cloud that we've shown, as well as a digital surface model and a digital terrain model. And utilizing these two, we can create a canopy height model, which we'll discuss in the next slide. And this is a key point in which we're going to be utilizing to find out our analysis for the gaps, as well as the overall forest health. So yeah, the point cloud generation stage basically boils down to us creating our canopy height model. And our canopy height model is our digital surface model, which is a modeling of the forest canopy, subtracted by a digital terrain model, which is a model of the ground. So yeah, subtracting these two, we get a good understanding of all the tree heights, like a tree elevation map. And yeah, so as an input to this, we take in our pre-processed image set, as well as a LiDAR-based digital terrain model, as well. We actually don't want to use the WebODM one because the WebODM digital terrain model, because we have such a thick canopy, it's kind of hard to disambiguate really what's accurately the ground. So this LiDAR allows us to have a good understanding of actually where the ground is, and we get a good recommendation on what to do next. So yeah, as an output, we get our point cloud, our digital surface model, as well as our canopy.
So using these models, we are able to find gaps within the canopy. Now, these gaps are important for forest regeneration and also a possible indicator of root rot. For our project, we decided to use a canopy height of 26 feet. And what that basically means is anything below, we would classify as the ground, and anything above would be classified as a canopy. To automate this step, we created a pipeline script that takes in the canopy height model and outputs a model with the gaps highlighted in green.
Once we have our canopy height models, we basically use this to make our pre-approximate object models. And the reason we make this model is because we fly our drones to the top of the canopy. And because of that, in our images, there's going to be a lot of these smaller and subordinate trees that are going to be hidden behind these like bigger and dominant trees. And so instead of trying to segment these trees individually, we try to segment them as clusters of trees or clumps of trees to give us like more of an accurate result. And then to do this, we basically use an algorithm given to us by one of our sponsors, Brian Fuentes. We simply use our generated canopy height models, input that into the algorithm in our studio, and that gives us our DAO models as an output.
So now moving on to results. Here's a demonstration of our pipeline in action. So this is the code that we developed. So right here, we're booting up the WebODM software. We're going to use point cloud generation, as well as our user interface. Then we're going to specify a specific pre-config for the parameters we're going to use for our point cloud generation, and then slap our images. During this time, we're creating our digital terrain model, digital surface model, as well as find our canopy height model and do our gap analysis. After this, and we have in-house, we have our results here where they can actually view these as quickly, see what's going on, change the color map, so basically the coloration of the key map they're working with, as well as a text file of the gap metrics, like the average area and everything, as well as a visual representation of what the gaps look like. So right here, it's just an image set of like 20 that we utilize of the north part of our site. So it's kind of a little janky, but good demonstration. And then also a big thing is providing the WebODM quality report, which basically shows how well we were actually able to generate our point cloud for debugging purposes for our sponsor.
All right, now moving on to our canopy height model results. We showed just the northern half of Landsberg Park, and all of these are on the same scale, starting with the LiDAR-based canopy height model, followed by the models generated using our 300-foot altitude surveys at 90 and 70% overlap, then followed by the 400-foot models at 90 and 70% image overlap. Overall, we found that models generated using flight altitudes that were the same generated relatively similar results, whereas the models using different flight altitudes, including 300 and 400, produced relatively different results. Additionally, we found that the LiDAR survey appeared to be the most similar to our 300-foot altitude survey, potentially because the drone was flying closer to the canopy. Next, we want to highlight the LiDAR survey in comparison to the 300-foot 90% image overlap canopy height model. And overall, we found a change in canopy height over time. The LiDAR survey produced a maximum canopy height of 186 feet versus our 300-foot altitude survey produced a model with a max height of 219 feet. And this may be due to the LiDAR misdetecting the tops of the trees, whereas our drone survey was able to capture the tops of the trees. However, Douglas fir have a typical growth rate between 1 to 3 feet per year, and so some of this difference in elevation may be due to tree growth over time. Next, in order to compare the impacts of altering flight parameters such as percent image overlap, we decided to compare our 300-foot models using the 70 and 90% image overlap canopy height models. We did this by subtracting one from another, and here's a histogram displaying the results with the elevation difference in feet on the x-axis, and then the millions of pixels representing our canopy height model on the y-axis. We found that most pixels have an elevation difference between 0 to 10 feet, with an average difference of 2.1 feet. Overall, this indicates that there was not a significant difference between the canopy height models generated using 90 and 70% image overlap, suggesting that image overlap of 70% could be used and could potentially still provide reliable results.
Here are all the models with the gaps highlighted in green. To your left, you have the LiDAR survey. To the far right, you have both 400-foot flights, which look very similar regardless of the overlap used. However, the same thing can't be said for the 300-foot flights, which is something I'll get into next. So looking more closely at the 300-foot at 90%, you can see that there's an overclassification of the forest, whereas the 70% actually underclassified the forest. Now, one of the reasons we believe this happened is due to the drone flight. When we fly lower to the canopy, we have an increased resolution, overall just making the 300-foot flights more sensitive to our height threshold. Finally, comparing the LiDAR survey to our 400-foot at 90% overlap, we chose to compare these two because we felt they gave the most accurate representation of gap change over time. And over the past 4 years, the gaps have expanded, increasing from 18 to 35%. In addition, some small individual gaps in the LiDAR survey have been merged together to create larger gaps in our survey. So this is a possible indicator of root rot, or as our survey was conducted in February, some of the understory vegetation may have fallen off, affecting our results.
Moving on to the results of our tree approximate object modeling stage. The top model that you see is from our LiDAR-based model, a LiDAR-based DAO, and the bottom model is a drone-based DAO of our site. And basically, the polygonal shapes that you see in both of those models are the actual clumps of trees that I was talking about, whereas the dots, the points, are those highest treetops or the highest points of those trees in those specific clumps. And visually, and based on our comparisons too, the main difference we saw in both of these models was that the LiDAR-based model has a lot more points, is a lot more dense, and some of these points also seem to be inaccurate. And the reason we think that happened is because the algorithm we used was actually built specifically for drone-based surveys. And because LiDAR models are a lot more high resolution, it might have caused like the algorithm to be confused and confuse some like branches or like other points as treetops, and hence overclassifying the canopy to some extent.
With our tree approximate objects, we were able to derive forest metrics. We started by finding correlations between measured tree height and other forest properties such as diameter breast height, basal area, and biomass using King County's plot inventory. We then found the tree approximate objects in each plot using a complex method that involved finding the angle between each plot center, as shown on the right, and each tree approximate object. We then used our height-based correlations and our tree approximate object heights to estimate each of our forest metrics, and then we compared averages between our estimates and ground-based data for each plot. This is an example of one of our height-based correlations where we compared height and biomass from King County's plot inventory, and then used the resulting equation with our tree approximate object heights to find the biomass of each tree approximate object. And this is our comparison between ground-based estimates and our derived estimates for average biomass per plot. As you can see, there's a strong correlation with an R-squared correlation coefficient of 0.75, where 1 indicates a perfect correlation. Additionally, we found similar values for our average biomass per plot, where the ground-based estimates were 130 tons and our best estimate was 155 tons.
Now to answer the project questions that we mentioned earlier, the first being, what are the ideal flight parameters? We found that flying 100 feet above the canopy or at an altitude of 300 feet gave the best representation of our forest. And for image overlap, we found that decreasing this was allowing us to decrease the flight times and also the noise in our images, which helps to increase the accuracy of our models.
And then for our second question, can we derive valid data from our methods? We found that yes, there was a strong correlation between both derived and measured forest metrics.
So to kind of wrap up, we successfully were able to develop an accessible as well as maintainable software, or sorry, a pipeline in which resilient forestry and its future analyses can utilize for their forest or environmental consultations.
And finally, overall, we found an increased gap area from the LiDAR survey conducted in 2021 to our drone surveys conducted in 2025. This may be explained by the laminated root rot that impacts Landsberg Park, as well as other natural events such as the November 2024 windstorm. To address the overall forest conditions within Landsberg Park, it is recommended to increase the structural diversity, particularly at the southern part of the forest, where the forest is most dense. This may be done through a variable density thin, where the trees can be thinned throughout the southern area, and then also by planting native root rot resistant trees such as western red cedar, and this can encourage forest regeneration throughout the site as well as increase the overall forest resiliency. Thank you so much, and we would love to take your questions.
So you used a 2-second sample rate for the drones when the pictures they were taking or the LiDAR they were doing. Could you increase that rate and decrease the overlap necessary for the flight path?
Yes, you can. We used a software called DroneLink, and typically automatically it sets it to 2 seconds for each image or between each image. And it also allows you to increase or decrease the image overlap however much you'd like. And this could help with decreasing the flight times or the image overlap as well, instead of doing the one or the other. But we didn't have time to test that for sure.
Any other questions?
Yeah, that was a really interesting, cool project. I'm wondering, due to the height of the trees, did you face any challenges for the ground control points in terms of visibility or the GPS OS that you used to find the coordinate of the points?
Luckily, there were a lot of gaps in the forest, so we had a lot of places that we could put the ground control points that would still be visible from the drone.
Also to add to that, the gaps were kind of dispersed around the site that we're working with, so it was nice because we didn't have a lot of localized ones on the top, like the northern part of our site. So they're pretty spread out, all things considered. And from our analysis, we kind of observed that if the GCPs weren't, that's kind of where the problems started kind of arising and everything. So yeah, it was a good kind of thing we observed.
I can talk pretty loud if you want.
So you set the canopy elevation at 26. That's a rather specific number, not 25, not 30. Why'd you end up at 26 out of curiosity?
Yeah, so we originally decided that we were going to test multiple different maximum heights. So we tested 3, 5, 6, 8, and 10 meters. And then to keep it consistent, we wanted to use feet. So by looking at all of the models we generated using those different maximum heights, 8 meters seemed to be the best representation of the gaps within Landsberg Park. And so we converted that to feet. So that was 6 feet.
Right, let's thank you, the presenters.
You start out with me. It was kind of that. You know, I mean, we're talking about how we're gonna. You're crazy. And it's really hard to communicate with her and all that. Understand each other and I kind of know what we're talking about.
No, no.
And I also so it's really nice having them to communicate with her. I'm trying to solve it. All right. I've been able to why it's been really cool even learning why my home is a destination is how we
I have been all of that. It's really.
I'm sorry.
Absolutely, yeah, yeah.
Yeah, because you're. I know he left.
Yeah, are you? Yeah, no, I'm gonna go talk to them a little.
Stay with us. So next team is a microgrid design tool.
Yeah. Hello, everyone. We are Team CS 2510 Microgrid Toolkit. We created this sponsored by KiloWatts for Humanity and SEDC. Before we begin, I'd like to introduce our staff. We have Jules, Jose, John, and myself, Jessica. Our primary sponsor is Dr. Peter Downhauer from KiloWatts for Humanity and Daniel Mausner, our technical lead. We also have Rob Nether, our SEDC sponsor, and Dr. Burkhard Engler, our advisor. We are so incredibly thankful for their guidance, support, and feedback this year. Thank you once again. Our sponsor is KiloWatts for Humanity. They are a volunteer-run nonprofit aiming to end energy poverty by designing and building customized energy toolkits. Our second sponsor is SESDC. They stand for the Sustainable Energy Solutions for Developing Countries. They are a member of the IEEE, which provides the technical expertise needed to install these microgrid toolkits. Now I will pass on to Jules to talk about the problem we are trying to solve.
Thanks, Jessica. So according to the World Health Organization, 685 million people were living without electricity in 2022. This number having increased for the first time in over a decade. This global energy access gap worsened as population grew at a higher rate than that of new electricity connections. The goal of KiloWatts for Humanity and SESDC is to provide sustainability by fostering strong organizational connections and develop small renewable systems. Other tools for microgrid development exist, but they have a steep learning curve and they can be expensive to use. So KiloWatts for Humanity states that alternatives are needed for projects like Keta and others, where the existing software limits who can access the software and also how reflective the results are to practical operational considerations that might differ a lot from lab conditions. Thus, the opportunity in this project is to improve microgrid design software to be accessible and realistic to its predictions, or in its predictions. Our project is important because each area has unique weather data and unique weather patterns. And this simulation helps to determine the energy generation based on each area's unique weather data, like irradiance, solar, wind patterns, and such. The simulation determines an estimate for the cost of the microgrid over 20 years to aid in business plans. And in this way, our project can easily provide data to investors and give an idea of what the energy generation and financial expense might look like. I'll pass it.
All right, so for the MVP, there was 5 main points that we wanted to go over with our sponsor, 5 areas that we wanted to address. The first one being, we wanted the tool to be very intuitive. That being said, just follow a simple process of creating a project, being able to input data based off of your needs, and then following that, being able to run the simulation, analyze the data, and be able to export it. Alongside with this, we wanted to implement a couple more features to make the simulation that the previous team had a bit more accurate and give it a bit more depth. So to do that, we incorporated an API that pulled data from, data specifically for Africa regarding solar, temperature, and wind speeds. And included in all this, we also wanted to make the project management very easy for everybody. So we know that when working on projects like this, it's important to collaborate and to share. For that reason being, we implemented users so that people can have their own account, share, and collaborate on the same projects. And then the fourth thing that we wanted to do was increase the analytics. So the previous team had just sole year, like 1 year projection, and that's not enough when we're thinking long-term. So we wanted to expand on that in all aspects in solar, temperature, wind, just so that investors could have a better idea of what it is they're looking for in the future. And the last thing, like we mentioned, there's a lot of microgrid toolkits that exist, but the thing that really makes it difficult is that there's not that easy access toolkit, you know, and that's what we were trying to really focus a lot of time and energy on. And we implemented a user guide that guides you through just about everything, even in terms of like inputting data. What is the data that I'm inputting? What is this like related to? And that's what we implemented the user guide for. So even if you guys wanted to, we haven't yet deployed it officially onto a website, but the second we do that, you guys can go ahead and go on there and you'll be able to test it out for yourself, see, hey, maybe I'm a little curious. I got some extra money. Let me see what I can do with it. Yeah, so I'm gonna go ahead and pass it on to Josh, who's gonna go over the technology used.
Hello, everyone. Yeah, like Jose said, I'll be going over the technology that we used in our project and also why we used it. So to start, we used Visual Studio Code as our code editor. It's just a simple code editor that provided all the functionality that we need to edit our code. Secondly, GitHub. We use GitHub for versioning, managing code, and also sharing code. And then also, since we all worked on different parts of the project, there were times where we all needed to merge our code, and GitHub made it really easy to do that. And then Firebase. Firebase provides all of our backend implementation for the project. So there's a couple applications that we used from Firebase that I'll talk about later. And then HTML, JavaScript, CSS. We had all in the past worked with these three, so it made it really easy to develop a website. And then Python, last year's group provided us with scripts or Python scripts, so we just built off those with Python. Next slide, please. And then we will all be talking about the solution. Like I said, we all worked on different parts, so I'll start by going off about the part that I worked on, and then I'll hand it off to Jose, and he'll talk about the API. So yeah, like I said, I worked on the back end. This was the main role that I had, was implementing Firebase into our project. And so this was just implementing the back end processes, like things like Google authentication, which allowed for secure user sign-in. Google Firestore stored all of our non-file-link data. Google Functions allowed us to run the Python backend scripts inside of our website. And then Firebase bucket storage held all the users' file-like data, so things like CSVs and images. And then finally, Google Hosting allowed us to host our website. And then I'm handing off to Jose, and he'll talk about the solar radiation API, or weather API.
Yeah, so we needed a way of, or out of curiosity, does anybody happen to know what the current wind speed is in Zambia? I don't think so. For that reason, we needed an API to get that necessary data, you know, at the intervals that we needed. So we went with the National Solar Radiation Database. This was very helpful because it had it at 30-minute intervals, and that's very specific for what we needed. And with that, we were able to get the necessary data, specifically irradiance data. Solar and wind data is a bit more easily accessible, but that's the reason why we chose this database specifically. After getting the database, we needed a way of having you guys be able to access it, you know? So what did we decide to do? We implemented a simple coordinate feature. So another thing, it's not very easy to know off the top of your head where exactly you're gonna try to implement any of these energy kiosks. So working with the front end and with the back end of it, we together were able to like put a little map so that users could simply click or like look around and get the coordinates for the specific area where they were considering working with. And not only that, you can also implement or you can incorporate it manually. So if for some reason you do have exact coordinates where you need to be working with, we can do that as well. And then the last thing that we needed to do with this was use those coordinates, pull that data and implement it into the previously working simulation to kind of give it that more depth and a bit more information so we could export better graphs in terms of years and data.
All right, I'm going to talk a bit about the scripts. So like we mentioned before, we inherited some legacy code from a previous electrical engineering team. This included calculations for solar power output, as well as wind energy generation and diesel energy generation. All of these calculations were done in kilowatts, or in watts. And so one of our jobs was to convert these to kilowatts and just generally consolidate and improve the performance of that legacy code. In addition to unit conversions, we also did some memory optimization on what we had, especially as we were extending it to more and more years. And we also generated graphs for a visual component using Matplotlib. We added some other calculations as well. So we implemented a battery with curtailment. So battery caps at a maximum and won't charge past its maximum, as well as load serviced and not serviced based on an input load that's read directly from the computer. And finally, we have customizable losses on a lot of our calculations. So these include things like temperature, wiring, aging, dust, dirt, and conversion losses that would be realistic problems in the field. I'll pass to Jessica to mention the front end. Thanks, Jules. For the front end, we essentially had to build it from scratch. Our sponsor required that it was responsive and user intuitive, especially for non-technical users, so people like you and me. They also required that it was desktop and mobile compatible, which is especially useful for when users are using it on-site during microgrid installations. Now I'll pass it back to Josh to talk about future implementation.
All right, hello everyone. So I'll talk about the future implementations. These are things that we missed that we couldn't get to, but that we hope the next group works on and implements it into our application. So to start with the back end, we would like more security features, project sharing functionality. So currently, not everything is shared when you share it with someone else in the project. And then improved load input querying. So right now, there's 24 different inputs for each hour of the day. And so we would like to improve that and make it a little bit more user-friendly because inputting 24 different things is not very fun. And then for the front end, loading indicators for the simulation, just to see when it will be done, when the simulation will be done running. And then also strengthening mobile responsiveness. Right now it works on mobile, but it's not amazing. So we'd like to improve that. And then for the scripts, cycle charging, and then also optimizing energy for different demand scenarios. And then finally, for the API, allowing for user selection of data. So if the user wants to specify a different region, right now the API only pulls from weather data in Africa. So if the user wants to specify that they want to pull from a different location, then they should be able to do that. And then finally, expanding the API range, kind of similar to what I just talked about. And then I will hand it off to Jules for a live demo.
All right, we're going to do a live demo. So welcome to the Microgrid Toolkit. We have an about page that sort of goes over the purposes of the tool, some background on our sponsors, as well as some background on the Seattle University Capstone project. We have a contact form for people to send messages. We have a detailed user guide walking people through setting up a project and customizing their project. It's scrollable and lookable. You're here. Like we mentioned, we're using Firebase authentication. If you don't have an account, you can register and it will send an email confirmation, but I already have an account, so I'm just going to log in. When you log in, it will take you to your dashboard. You have the opportunity to create a project, so I'll create a demo. And add a description. And you can also share projects, so you can click to add an email address or remove that email address. And you can also delete projects. It will double check that you actually want to delete your project before it deletes it. Let's go to our demo. We have the option for a manual latitude longitude input or a CSV input, where you can upload a CSV containing the values for radiance, temperature, wind, etc. We'll do a manual input, and I'm going to put generic location or lat long for Zambia. So this is minus 1530. You can customize your battery. So we have lead acid and lithium ion. This determines the minimum threshold so that batteries aren't charging past a point where it will significantly damage the battery. Lithium ion has a lower threshold, so we're going to use that. And charge capacity per hour for the battery, maximum storage. You can add a generator with generator max output in kilowatts. Add a solar panel, customizing the array size as well as the losses. These are auto-filled, but you can edit them. And finally, the wind turbine, you can set a number of turbines and set their rated power. And customize the cut-in speed, cut-out speed, and rated speed at your timeline. About this. Then you can save your inputs and run the simulation. So I did click that. It's going to take a minute to run, so I'll walk you through the graphs first. When you run the graphs, we'll output the solar generation over 1 year, as well as some maps of the heat maps. This is a nice one of the average daily solar power generation by month and day. Here's a 20-year projection of that solar output, and you can see a slight degradation due to losses. We'll get finished. We can go over that later. Here's a load profile. This is being read in just to save us the time of 25. Okay. And load growth and wind projections. You're running out of time. So, the output slots, you can print them to PDF as well to see those graphs. So here's the output. Project graphs. And that is the Microgrid toolkit. Thank you all for listening. Questions?
Thank you very much. What was the greatest technical challenge each of your parts of the project faced?
I think one of our big challenges was collaboration and like utilizing GitHub properly. I know for many of us, like we didn't merge as much as we should, but it turned out good in the end.
Speaking on my behalf, I think it was just the learning curve. So we're for the most part all CS majors, and we're not really too we didn't have a background into what was being wanted from us with all these data values. So it was kind of taking a bit of time to like actually learn what it is that we're doing, what data we're trying to receive, and for what reason. Like all the graphs that you saw, each one alone can take a good amount of time and just really understanding. I think I'll pass it to Julie so we can collaborate with you.
Yeah, sure. I think the biggest challenge for me and us generally were course issues, especially as I was expanding simulation to run for more than 1 year, or encountering memory, basically hitting memory caps. I was returning course 500 error, and the simulation was starting to time out, and navigating using or sending these HTTP GET and POST requests back and forth with the server was causing issues, but we did end up resolving this. That's great. I think Josh will talk probably more about cores.
I think for me, it was just like understanding all the things about just the web infrastructure. So there was a lot of like applications in the cloud service that I just didn't know about, and it would have saved a lot of time for me if I knew about these things. So yeah.
Maybe one more question? All right, then let's thank you.
Yeah, but everybody.
The project is leveraging AI with the published scientific article for database cycle.
Hi, we are the computer science capstone team for Earth Economics. I'm Michael, and I have been working on this project in collaboration with Cassidy, Liam, Kui, and Hadia. Additionally, we have been working in collaboration with our sponsor liaison, Angela Fletcher, and our faculty advisor, Professor Susan Reeder. Earth Economics is a nonprofit organization founded in 2004 and located in Tacoma, Washington. Their mission is to quantify the benefits of nature for decision-making. Their vision is to use this to cultivate a world where nature and the environment are essential to all economic decision-making. Earth Economics currently maintains a database of many scientific articles, and their main problem is that building this database requires lots of manual work, particularly with data extraction from the articles. And the main question that we are addressing with our project is, how can we reduce this manual labor? To do so, we have been using AI to analyze the articles automatically, since this is one of the biggest consumers of time for our sponsor. And automating this important task would allow them to spend much more time on meaningful analysis. And to go further into the development and design for our program, I will be handing it off to Liam.
Yeah, thank you, Michael. Yeah, so here's our, we identified those components as our minimum viable product. And first and foremost, we wanted to utilize AI model to do the hard work for us, as Michael mentioned before. And also we wanted to have a user-friendly UI. And also ultimately, most importantly, we wanted to generate a CSV file, which then can be uploaded to the database. And we wanted to have the data analysis, which evaluate model and system performance, and also want to have the user manual and documentation. And moving on to our solution to our MVP. So first, we take the large language model as a choice of AI, which is more specifically GPT 4.0. And using the prompt engineering, we use to scan the research paper and do the data extraction into a spreadsheet. And then also we developed the data pipeline, which includes like file management system and also AI module. And we hide those complexity into we hide those complexity and have developed the UI, and which will then be deployed onto our staff members' desktop. And we first chose to go with which we first thought of like deploying our app onto the desktop, website, but then we faced like security vulnerability and also it wasn't cost efficient. So we then decided to go with the desktop application. And these are the tools that we have used. The right-hand side is for the data analysis part, and also these are for our developments. And I'll be passing off to Cassidy for our diagrams.
Yeah, thanks, Liam. We have a couple diagrams that go more into depth about our project implementation. Here we have our data diagram, which shows the flow of data through our application. Because it's a pipe and filter architecture, that means data will flow through the pipeline from the user and get outputted into their desired format. We start at the top left corner here. The user or researcher will input data, which is just PDF research papers. This data gets validated and text is extracted from these research papers. It is sent to our AI system, which returns results that need to be formatted into our desired CSV format. That is returned to the user. We also have our component diagram here, just to emphasize the modular design approach we used for this project. So as you can see, there are three main big components to our project. We have our user interface, our AI module, and our file manager. And having a modular component-based design just means that all of our components are pretty independent from each other. Logically, this means that things like our user interface is separate from our actual processing logic. So our processing is not dependent on the desktop application front end we chose. We also have our deployment diagram, which shows not only the flow of data through the application, the modularity, but also the application in relation to the user. Like Liam was mentioning, a big design decision for us was the choice to use a desktop application and not like a website you can access online. And because this application is for use within the company in-house, it didn't make sense from a security standpoint to just have it on the web. And it also is more cost efficient to have a desktop application, as we can deploy and distribute the application through executable files and set it up with the analysts at the company that way. Now I'll pass it off to Hui, who will talk about our solutions performance.
Thank you, Cassidy. So my name is Hui, and I was responsible for the system performance and the load testing of the application. So our client really cares about the app's accuracy and reliability. However, they also care about the speed and load capacity as well. So in this project, we tested with two advanced AI models. We have GPT 4.1 Nano for speed and cost efficiency, and we have GPT 4.1 for intelligence. So you will notice here that with one single complex paper, GPT 4.1 Nano took about 25 to 40 seconds. As we increase the load to, let's say, 20 papers, GPT 4.1 Nano took about 9 minutes to almost 10 minutes. And GPT 4.1 took about 11 minutes. So 1 or 2 minutes difference here. So even though the time difference will grow with more papers, the key takeaway here is that even though without immediate optimization, this app can already process data much, much faster than I believe a human could possibly can. So in the next slide, equally important is that we understand the system load capacity. So for this experiment, we only use GPT 4.1, and this model can handle up to 1 million tokens, or in other words, you could say 1 million units of text in one pass to the model. However, so this might suggest that the system can handle up to 40 to 60 papers. However, that's a rate limit of 30,000 units of text that can be sent to the model in one pass. So our recommendation would be to process papers in a batch of, let's say, less than 10 papers to ensure optimal performance and avoid the input being cut off. So to summarize, I think this is going to be a great significant gain for our clients. And the goals for these type of testing is to help them define operational boundaries and help guide efficient usage. In the next slide, we want to show the app in action. So this is the user interface of the app. The users can select and deselect research papers as they like. However, the app is only supporting PDF paper right now. As for our sponsor needs, a lot of their data and documents are in PDF formats. But we do hope to support more document type in the future, such as multiple type of images. So when the user is happy with the selection, they can click the process button here, and the papers will be sent to the backend system for processing. And I believe this paper took about 20 seconds, as mentioned in the previous slide, 25 or a second, depending on the complexity of the papers. So upon completions, the users can choose to click a download button, which will save their template into their local file, their local folder, or they can choose to click a button, return to home if they don't like the result and wish to do another run. So that's our demo, and in the next slide, we want to show how the results look like. Right. So this is how the results look like after we run an experiment of 10 papers, and it looks like this part of the CSV file is completely filled out, which is lucky for us. However, I mentioned that reliability and the app accuracy is also very important to our sponsor. Therefore, I will pass on next to Hadi to talk about accuracy testing and results.
Thank you, Reed. So our main objective was to streamline clerical tasks and reduce the manual labor involved in having to go back and so reduce latency in database population process. Specifically, after our AI model produced the CSV, we didn't want them going back to have to correct it. And so the way we achieved that was we conducted rigorous accuracy and reliability testing. Specifically, we compared cosine similarity scores between accuracy between values that were expected, which were already in the populated search database, and values that our AI model derived. This picture over here highlights one specific paper that we ran with an average cosine similarity score of 87%. And for bibliographic fields, so we had three main fields, categories that we were testing accuracy for, which was bibliographic data, ecosystem data, and land valuation data. For bibliographic data for this paper, we had a 99% accuracy. For ecosystem data, we had 77% accuracy, and for land valuation data, we had an 80% accuracy. So overall, for all of the papers that we tested, between expected and derived values, we had a 92% accuracy score for bibliographic data. For ecosystem descriptor fields, we had a 64% accuracy, and for valuation fields, we had a 60% accuracy rate. With that in mind, from all the progress we've made, I'd like to talk about the milestones we've achieved from our MVP. So firstly, we managed to create an AI-powered end-to-end data extractor tool paired with a friendly user interface where users can upload papers, view its progress, and also view the output produced by our AI backend. So the output from that is a filled Excel sheet matching the template provided to us, which is compatible for import to the served database. For efficiency, we also conducted an analysis of the model and system performance testing and system load testing. And finally, for ease of transition for our final deployed product, we also provided a user guide. Yeah, so we've also identified key avenues our system has the potential to develop into. So we could, firstly, what we could do is provide a backend solution, provide a backup AI model. So currently our system is set up to only support OpenAI, but we could also introduce other providers such as Llama's Meta
Meta's llama model. Or we could also allow users to parse different types of documents other than PDFs, such as a Microsoft Word doc or other types of data, such as graphs, or images. Yeah, lastly, we'd like to thank our sponsor, Earth Economics and Angela Fletcher, for providing us with the opportunity to work on this, and Professor Susan Reeder, our faculty advisor, Leonard Matthias, our professors and peers, Project Center, and finally all my teammates for working so hard throughout the year. And I'd like to open the floor for any questions.
Some fields had more accurate results than others. For example, the ecological data versus the other types. One had 99%, the others had 60 and 64.
Yeah, so based on these sections, we had targeted different accuracy rates because for things like research papers, things like bibliographic data is formatted pretty much the same across all research papers. So finding things like the author, the title, it's pretty easy and pretty consistent. Things like ecosystem and valuation data vary per paper. Also, our database entry has over 200 fields in it. Not all of those need to be filled out if there's no such information in the paper. So based on these things, we had lower targets for these, especially because the model we chose had to balance both cost efficiency and like intelligence and reasoning. Questions?
I wasn't sure if it was app or covered, but why did you guys choose to go with OpenAI instead of all other conventional?
Yeah, so in our exploratory phase in the first quarter of the school year, we tested a bunch of different models and made like a lot of little dummy applications to test them. And OpenAI at that time performed the best, and it also had like a pretty significant like documentation. It was in the fall, a pretty big contender in the industry, so we decided to use there.
Thank you for the question. So I want to say a little bit about this. So even though like OpenAI is like the most advanced model out there, they just released the 4.1 version. We also have like a backup solution because like this OpenAI is a provider, so it can fail anytime. So we have the option from it's an advice from industry reviewer to try out Gemini and Llama. So in the future plan, we're definitely gonna implement multiple models to prevent the disaster or failures and make sure that the app is available most of the time.
Other questions? Right, let's thank the presenter.
Outside there are posters and also the posters on the second floor as well. And I hope you enjoy those posters and looking for our excellent students. Hope there are some afternoons.
So good. Here you are.